Chapter 12, Part 2 of Industrial Biography. Ironworkers and Toolmakers by Samuel Smiles. This LibriVox recording is in the public domain. Recording by Clive Catterall. Henry Maudslay, Part 2. One of the first uses to which Mr. Maudslay applied the improved slide rest, which he perfected shortly after beginning business in Margaret Street, Cavendish Square, was in executing the requisite tools and machinery required by Mr. (afterwards Sir Mark Isambard) Brunel for manufacturing ship's blocks. The career of Brunel was of a more romantic character than falls to the ordinary lot of mechanical engineers. His father was a small farmer and postmaster at the village of Hackville in Normandy, where Mark Isambard was born in 1769. He was early intended for a priest, and educated accordingly. But he was much fonder of the carpenter's shop than of the school, and coaxing, entreaty, and punishment alike failed in making a hopeful scholar out of him. He drew faces and plans until his father was almost in despair. Sent to school at Rouen, his chief pleasure was in watching the ships along the quays, and one day his curiosity was excited by the sight of some large iron castings just landed. What were they? How had they been made? Where did they come from? His eager inquiries were soon answered. They were parts of an engine intended for the great Paris waterworks. The engine was to pump water by the power of steam, and the castings had been made in England, and had just been landed from an English ship. "England!" exclaimed the boy. "Ah, when I am a man I will go and see the country where such grand machines are made." On one occasion, seeing a new tool in a cutler's window, he coveted it so much that he pawned his hat to possess it. This was not the right road to the priesthood, and his father soon saw that it was of no use urging him further. But the boy's instinct proved truer than the father's judgment. It was eventually determined that he should qualify himself to enter the Royal Navy, and at 17 he was nominated to serve in a corvette as volontaire d'honneur. His ship was paid off in 1792, and he was at Paris during the trial of the king. With the incautiousness of youth, he openly avowed his royalist opinions in the café which he frequented. On the very day that Louis was condemned to death, Brunel had an angry altercation with some ultra-republicans, after which he called to his dog, "Viens, citoyen." Scowling looks were turned upon him, and he deemed it expedient to take the first opportunity of escaping from the house, which he did by the back door, and made the best of his way to Hackville. From thence he went to Rouen, and succeeded in finding a passage on board an American ship, in which he sailed for New York, having first pledged his affection to an English girl, Sophia Kingdom, whom he had accidentally met at the house of Mr. Carpentier, the American consul at Rouen. Arrived in America, he succeeded in finding employment as assistant surveyor of a tract of land along the Black River near Lake Ontario. In the intervals of his labours he made occasional visits to New York, and it was there that the first idea of his block machinery occurred to him. He carried his idea back with him into the woods, where it often mingled with his thoughts of Sophia Kingdom, by this time safe in England after passing through the horrors of a French prison. "My first thought of the block machinery," he once said, "was at a dinner party at Major General Hamilton's in New York. My second under an American tree, when one day I was carving letters on its bark. The turn of one of them reminded me of it, and I thought, ah, my block, so it must be." And what do you think were the letters I was cutting? Of course, none other than S.K. Brunel subsequently obtained some employment as an architect in New York, and promulgated various plans for improving the navigation of the principal rivers. Among the designs of his which were carried out was that of the Park Theatre at New York, and a cannon foundry, in which he introduced improvements in casting and boring big guns. But being paid badly for his work, and a powerful attraction drawing him constantly towards England, he determined to take final leave of America, which he did in 1799. And landed at Falmouth in the following March. There he again met Miss Kingdom, who had remained faithful to him during his 6 long years in exile, and the pair were shortly after united for life. Brunel was a prolific inventor. During his residence in America he had planned many contrivances in his mind, which he now proceeded to work out. The first was a duplicate writing and drawing machine, which he patented. The next was a machine for twisting cotton thread and forming it into balls. But omitting to protect it by a patent, he derived no benefit from the invention, though it shortly came into very general use. He then invented a machine for trimmings and borders for muslins, lawns, and cambrics, of the nature of a sewing machine. His famous block machinery formed the subject of his next patent. It may be explained that the making of the blocks, employed in the rigging of ships for raising and lowering the sails, masts, and yards, was then a highly important branch of manufacture. Some idea may be formed of the number used in the Royal Navy alone from the fact that a 74-gun ship required to be provided with no fewer than 1,400 blocks of various sizes. The sheaved blocks used for the running rigging consisted of the shell, the sheaves, which revolved within the shell, and the pins which fastened them together. The fabrication of these articles, though apparently simple, was in reality attended with much difficulty. Every part had to be fashioned with great accuracy and precision to ensure the easy working of the block when put together, as any hitch in the raising or lowering of the sails might, on certain emergencies, occasion a serious disaster. Indeed, it became clear that mere handwork was not to be relied on in the manufacture of these articles, and efforts were early made to produce them by means of machinery of the most perfect kind that could be devised. In 1781, Mr. Taylor of Southampton set up a large establishment on the River Itchen for their manufacture, and on the expiry of his contract, the government determined to establish works of their own in Portsmouth Dockyard, for the purpose at the same time of securing greater economy and of being independent of individual makers in the supply of an article of such importance in the equipment of ships. Sir Samuel Bentham, who then filled the office of Inspector General of the Naval Works, was a highly ingenious person, and for some years had been applying his mind to the invention of improved machinery for working in wood. He had succeeded in introducing into the royal dockyards sawing machines and planing machines of a superior kind, as well as block-making machines. Thus the specification of one of his patents, taken out in 1793, clearly describes a machine for shaping the shells of the blocks in a manner similar to that afterwards specified by Brunel. Bentham had even proceeded with the erection of a building in Portsmouth Dockyard for the manufacture of the blocks after his method, the necessary steam engine being already provided. But with a singular degree of candour and generosity, on Brunel's method being submitted to him, Sir Samuel at once acknowledged its superiority to his own, and promised to recommend its adoption by the authorities in his department. The circumstance of Mrs. Brunel's brother being Under-Secretary to the Navy Board of the time probably led Brunel in the first instance to offer his invention to the Admiralty. A great deal, however, remained to be done before he could bring his ideas of the block machinery into definite shape. For there is usually a wide interval between the first conception of an intricate machine and its practical realization. Though Brunel had a good knowledge of mechanics, and was able to master the intricacies of any machine, he laboured under the disadvantage of not being a practical mechanic, and it's probable that but for the help of someone possessed of this important qualification, his invention, ingenious and important though it was, would have borne no practical fruits. It was at this juncture that he was so fortunate as to be introduced to Henry Maudslay, the inventor of the slide rest. It happened that a Monsieur de Bacancourt, one of the French émigrés, of whom there were so many in London, was accustomed almost daily to pass Maudslay's little shop in Wells Street, and being himself an amateur turner, he curiously inspected the articles from time to time exhibited in the window of the young mechanic. One day a more than ordinarily nice piece of screw-cutting made its appearance, on which he entered the shop to make inquiries as to the method by which it had been executed. He had a long conversation with Maudslay, with whom he was greatly pleased, and he was afterwards accustomed to look in upon him occasionally to see what new work was going on. Bacquancourt was also on intimate terms with Brunel, who communicated to him the difficulty he had experienced in finding a mechanic of sufficient dexterity to execute his design of the block-making machinery. It immediately occurred to the former that Henry Maudslay was the very man to execute work of the elaborate character proposed, and he described to Brunel the new and beautiful tools which Maudslay had contrived for the purpose of ensuring accuracy and finish. Brunel at once determined to call upon Maudslay, and it was arranged that Bacquancourt should introduce him, which he did, and after the interview which took place, Brunel promised to call again with the drawings of his proposed model. A few days passed, and Brunel called with the first drawing, done by himself, for he was a capital draftsman, and used to speak of drawing as the alphabet of the engineer. The drawing only showed a little bit of the intended machine, and Brunel did not yet think it advisable to communicate to Maudslay the precise object he had in view, for inventors are usually very chary of explaining their schemes to others, for fear of being anticipated. Again Brunel appeared in Maudslay's shop with a further drawing, still not explaining his design. But at the third visit, immediately on looking at the fresh drawings he had brought, Maudslay exclaimed, "Ah, now I see what you're thinking of. You want machinery for making blocks." At this Brunel became more communicative, and explained his designs to the mechanic, who fully entered into his views, and went on from that time forward striving to his utmost to work out the inventor's conceptions and embody them in a practical machine. While still occupied on the models, which were begun in 1800, Maudslay removed his shop from Wells Street, where he was assisted by a single journeyman, to Margaret Street, Cavendish Square, where he had greater room for carrying on his trade, and was also enabled to increase the number of his hands. The working models were ready for inspection by Sir Samuel Bentham and the Lords of the Admiralty in 1801, and having been fully approved by them, Brunel was authorised to proceed with the execution of the requisite machinery for the manufacture of the ship's blocks required for the Royal Navy. The whole of this machinery was executed by Henry Maudslay. It occupied him very fully for nearly 6 years, so that the manufacture of blocks by the new process was not begun until September 1808. We despair of being able to give any adequate description in words of the intricate arrangements and mode of action of the block-making machinery. Let anyone attempt to describe the much more simple and familiar process by which a shoemaker makes a pair of shoes, and he will find how inadequate mere words are to describe any mechanical operation. Suffice it to say that the machinery was of the most beautiful manufacture and finish, and even at this day will bear comparison with the most perfect machines which can be turned out with all the improved appliances of modern tools. The framing was of cast iron, while the parts exposed to violent and rapid action were all of the best hardened steel. In turning out the various parts, Maudslay found his slide rest of indispensable value. Indeed, without this contrivance, it is doubtful whether machinery of so delicate and intricate a character could possibly have been executed. There was not one, but many machines in the series, each devoted to a special operation in the formation of a block. Thus there were various sawing machines, the straight cross-cutting saw, the circular cross-cutting saw, the reciprocating ripping saw, and the circular ripping saw. Then there were the boring machines, and the mortising machine, of beautiful construction for cutting the sheave holes, furnished with numerous chisels, each making from 110 to 150 strokes a minute, and cutting at every stroke a chip as thick as a pasteboard with the utmost precision. In addition to these were the corner saw for cutting off the corners of the block, the shaping machine for accurately forming the outside surfaces, the scoring engine for cutting the groove round the longest diameter of the block for the reception of the rope, and various other machines for drilling, riveting, and finishing the blocks, besides those for making the sheaves. The total number of machines employed in various operations of making a ship's block by the new method was 44, and after being regularly employed in Portsmouth Dockyard for upwards of 50 years, they are still as perfect in their action as the day on which they were erected. They constitute one of the most ingenious and complete collections of tools ever invented for making articles in wood, being capable of performing most of the practical operations of carpentry with the utmost accuracy and finish. The machines worked by a steam engine of 32 horsepower, which is also used for various other dockyard purposes. Under the new system of block making, it was found that the articles were better made, supplied with much greater rapidity, and executed at greatly reduced cost. Only 10 men with the new machinery could perform the work which before had required 110 men to execute, and not fewer than 160,000 blocks of various kinds and sizes could be turned out in a year, worth not less than £541,000. The satisfactory execution of the block machinery brought Maudslay a large accession of fame and business, and the premises in Margaret Street proving much too limited for his requirements, he again resolved to shift his quarters. He found a piece of ground suitable for his purpose in Westminster Road, Lambeth. Little more than a century since, it formed part of a marsh, the name of which is still retained in the adjoining street, its principal productions being bulrushes and willows, which were haunted in certain seasons by snipe and waterfowl. An enterprising riding master had erected some premises on a part of the marsh, which he used for a riding school. But the speculation not answering, they were sold, and Henry Maudslay became the proprietor. Hither he removed his machinery from Margaret Street in 1810, adding fresh plant from time to time as it was required. And with the aid of his late excellent partner, he built up the far-famed establishment of Maudslay, Field and Company. There he went on improving his old tools and inventing new ones as the necessity for them arose, until the original slide lathes used for making the block machinery became thrown into the shade by the comparatively gigantic machine tools of the modern school. Yet the original lathes are still to be found in the collection of the firm in Westminster Road, and continue to do their daily quota of work with the same precision as they did when turned out of the hands of their inventor and maker some 60 years ago. It is unnecessary that we should describe in any great detail the further career of Henry Maudslay. The rest of his life was full of useful and profitable work to others as well as to himself. His business embraced the making of flour and sawmills, mint machinery, steam engines of all kinds. Before he left Margaret Street in 1807, he took out a patent for the improvement of the steam engine, by which he much simplified its parts and secured greater directness of action. His new engine was called the pyramidal because of its form, and was the first move towards what are now called direct acting engines, in which the lateral movement of the piston is communicated by connecting rods to the rotary movement of the crankshaft. Mr. Nasmyth says of it that, on account of its great simplicity and great get-at ability of parts, its compactness and self-contained steadiness, this engine has been the parent of a vast progeny, all more or less marked by the distinguished features of the original design, which is still in as high favour as ever. Mr. Maudslay also directed his attention in like manner to the improvement of the marine engine, which he made so simple and effective as to become in a great measure the type of its class, and it has held its ground almost unchanged for nearly 30 years. The Regent, which was the first steamboat that plied between London and Margate, was fitted with engines by Maudslay in 1816, and it proved the forerunner of a vast number of marine engines, the manufacture of which soon became one of the most important branches of mechanical engineering. Another of Mr. Maudslay's inventions was his machine for punching boiler plates, by which the production of ironwork of many kinds was greatly facilitated. This improvement originated in the contract which he held for some years for supplying the Royal Navy with iron plates for ships' tanks. The operations of shearing and punching had before been very imperfectly done by hand, with great expenditure of labour. To improve the style of the work and lessen the labour, Maudslay invented the machine now in general use, by which the holes punched in the iron plate are exactly equidistant, and the subsequent operation of riveting is greatly facilitated. One of the results of the improved method was the great saving which was at once effected in the cost of preparing the plates to receive the rivets, the price of which was reduced from 7 shillings per tank to 9d. he continued to devote himself to the last to the improvement of the lathe, in his opinion the master machine, the life and soul of engine turning, of which the planing, screw-cutting, and other machines in common use are but modifications. In one of the early lathes which he contrived to be made, the mandrel was 9 inches in diameter. It was driven by wheel gearing, like a crane motion, and adapted to different speeds. Some of his friends, on first looking at it, said he was going too fast, but he lived to see work projected on so large a scale as to prove that his conceptions were just, and that he had merely anticipated by a few years the mechanical progress of his time. His large removable bar lathe was a highly important tool of the same kind. It was used to turn surfaces many feet in diameter. While it could be used for boring wheels or the slide rods of marine engines, it could turn a roller or cylinder 2 or 3 times the diameter of its own centres from the ground level, and indeed could drive roundwork of any diameter that would clear the roof of the shop. This was therefore an almost universal tool, capable of very extensive uses. Indeed, much of the work now executed by means of special tools, such as the planing or slotting machine, was then done in the lathe, which was used as a cutter shaping machine, fitted with various appliances according to the work. Maudslay's love of accuracy also led him from an early period to study the object of improved screw-cutting. The importance of this department of mechanism can scarcely be overrated, the solidity and permanency of most mechanical structures mainly depending upon the employment of the screw, at the same time that the parts can be readily separated for renewal or repair. Anyone can form an idea of the importance of the screw as an element in mechanical construction by examining, say, a steam engine, and counting the number of screws employed in holding it together. Previous to the time at which the subject occupied the attention of our mechanic, the tools used for making screws were of the most rude and inexact kind. The screws were for the most part cut by hand, the small by filing, the larger by chipping and filing. In consequence of the great difficulty in making them, as few were used as possible, and cotters and cotterils or forelocks were employed instead. Screws, however, were to a certain extent indispensable, and each manufacturing establishment made them after their own fashion. There was utter want of uniformity. No system was observed as to pitch, i.e. the number of threads to the inch, nor was any rule followed as to the form of those threads. Every bolt and nut was a sort of speciality in itself, and neither owed nor admitted of any community with its neighbours. To such an extent was this irregularity carried that all bolts and their corresponding nuts had to be marked as belonging to each other, and any mixing of them together led to endless trouble, hopeless confusion, and enormous expense. Indeed, none but those who lived in the comparatively early days of machine manufacture can form an adequate idea of the annoyance occasioned by the want of system in this branch of detail, or duly appreciate the services rendered by Maudslay to mechanical engineering by the practical measure which he was among the first to introduce for its remedy. In his system of screw-cutting machinery, his taps and dies, and screw tackle generally, he laid the foundations of all that has since been done in this essential branch of machine construction, in which he was so ably followed up by several of the eminent mechanics brought up in his school, and more especially by Joseph Clement and Joseph Whitworth. One of his earliest self-acting screw lathes, moved by a guide screw and wheels after the plan followed by the latter engineer, cut screws of large diameter and of any required pitch. As an illustration of its completeness and accuracy, we may mention that by its means a screw 5 feet in length and 2 inches in diameter was cut with 50 threads to the inch, the nut to fit on it being 12 inches long and containing 600 threads. This screw was principally used for dividing scales for astronomical purposes, and by its means divisions were produced so minute that they could not be detected without the aid of a magnifier. The screw, which was sent for exhibition to the Society of Arts, is still carefully preserved amongst the specimens of Maudslay's handicraft at the Lambeth Works, and is a piece of delicate work which every skilled mechanic will thoroughly appreciate. Yet the tool by which this fine piece of turning was produced was not an exceptional tool, but was daily employed in the ordinary work of the manufactory. Like every good workman who takes pride in his craft, he kept his tools in first-rate order, clean and tidily arranged, so that he could lay his hand upon the thing he wanted at once, without loss of time. They are still preserved in the state in which he left them, and strikingly illustrate his love of order, nattiness, and dexterity. Mr. Nasmyth says of him that you could see the man's character in whatever work he turned out, and as the connoisseur in art will exclaim at the sight of a picture, "That is Turner," or "That is Stansfield," detecting the hand of the master in it, so the experienced mechanician, at the sight of one of his machines or engines, will be equally ready to exclaim, "That is Maudslay," for the characteristic style of the master mind is as clear to the experienced eye in the case of the finished machine as the touches of the artist's pencil are in the case of the finished picture. Every mechanical contrivance that became the subject of his study came forth from his hand and mind rearranged, simplified, and made new, with the impress of his individuality stamped upon it. He at once stripped the subject of all unnecessary complications, for he possessed a wonderful faculty of knowing what to do without, the result of his clearness of insight into mechanical adaptations, and the accurate and well-defined notions he had formed of the precise object to be accomplished. Every member or separate machine in the system of block machinery, says Mr. Nasmyth, is full of Maudslay's presence, and in that machinery, as constructed by him, is to be found the parent of every engineering tool, by the aid of which we are now achieving such great things in mechanical construction. To the tools of which Maudslay furnished the prototypes are we mainly indebted for the perfection of our textile machinery, our locomotives, our marine engines, and the various implements of art, agriculture, and of war. If any one who can enter into the details of the subject will be at pains to analyse, if I may so term it, the machinery of our modern engineering workshops, he will find in all of them the strongly marked features of Maudslay's parent machine, the slide rest and the slide system, whether it be a planing machine, a slotting machine, a slide lathe, or any of the other wonderful tools which are now enabling us to accomplish so much in mechanism. And one of the things in which Mr. Maudslay took just pride was in the excellence of his work. In designing and executing it, his main object was to do it in the best possible style and finish, altogether irrespective of the probable pecuniary results. This he regarded in the light of a duty he could not and would not evade, independent of its being a good investment for securing future reputation. And the character which he thus obtained, although at times purchased at great cost, eventually justified the soundness of his views. As the eminent Mr. Penn, the head of the great engineering firm, is accustomed to say, "I cannot afford to turn out second-rate work." So Mr. Maudslay found both character and profit in striving after the highest excellence in his productions. He was a particular man, even in the minutest details. Thus, one of the points on which he insisted, apparently a trivial matter, but in reality of considerable importance in mechanical construction, was the avoidance of sharp interior angles in ironwork, whether wrought or cast, for he found that in such interior angles cracks were apt to originate. When the article was a tool, the sharp angle was less pleasant to the hand as well as to the eye. In the application of his favourite round or hollow corner system, as for instance in the case of the points of junction of the arms of a wheel with its centre or rim, he used to illustrate its superiority by holding up his hand and pointing out the nice round hollow at the junction of the fingers, or by referring to the junction of the branches to the stem of a tree. Hence he made a point of having all the angles of his machine framework nicely rounded off on their exterior, and carefully hollowed in their interior angles. In forging such articles, he would so shape his metal before bending that the result should be the right hollow or round corner when bent, the anticipated external angle falling into its proper place when the bar so shaped was brought to its ultimate form. In all such matters of detail he was greatly assisted by his early dexterity as a blacksmith, and he used to say that to be a good smith you must be able to see in the bar of iron the object proposed to be got out of it by the hammer or the tool, just as the sculptor is supposed to see in the block of stone the statue which he proposes to bring forth from it by his mind and his chisel. Mr. Maudslay did not allow himself to forget his skill in the use of the hammer, and to the last he took pleasure in handling it, sometimes in the way of business, and often through sheer love of his art. Mr. Nasmyth says, "It was one of my duties, while acting as assistant in his beautiful little workshop, to keep a stock of handy bars of lead, which he had placed on a shelf under his workbench, which was of thick slate for the more ready making of his usual illustrative sketches of machinery and chalk. His love of iron forging led him to take delight in forging the models of work to be ultimately done in iron, and cold lead, being about the same malleability as red-hot iron, furnished a convenient material for illustrating the method to be adopted with the large work. I well remember the smile of satisfaction that lit up his honest face when he met with a good excuse for having a go at one of the bars of lead with a hammer and anvil, as if it were a bar of iron, and how, with a few dexterous strokes, punchings of holes, and rounded notches, he would give the rough bar or block its desired form. He always aimed at working it out of the solid as much as possible, so as to avoid the risk of any concealed defect to which ironwork built up of welded parts is so liable. And when he had thus cleverly finished his model, he used forthwith to send for the foreman of smiths, and show him how he was to instruct his men as to the proper forging of the desired object. One of Mr. Maudslay's old workmen, when informing us of the skilful manner in which he handled the file, said, "It was a pleasure to see him handle a tool of any kind, but he was quite splendid with an 18-inch file." The vice at which he worked was constructed by himself, and it was perfect of its kind. It could be turned round to any position on the bench. The jaws would turn from the horizontal to the perpendicular, or any other position, upside down if necessary, and they would open 12 inches parallel. Mr. Nasmyth furnishes the following further recollections of Mr. Maudslay, which will serve in some measure to illustrate his personal character. "Henry Maudslay," he says, "lived in the days of snuff-taking, which, unhappily as I think, has given way to the cigar-smoking system. He enjoyed his occasional pinch very much. It generally preceded the giving out of a new notion or suggestion for an improvement or alteration of some job in hand. As with most of those who enjoy their pinch, about 3 times as much was taken between the fingers as was utilised by the nose, and the consequence was that a large unconsumed surplus collected in the folds of the master's waistcoat as he sat working at his bench. Sometimes a file or a tool, or some small piece of work, would drop, and then it was my duty to go down on my knees and fetch it up. On such occasions, while waiting for the article, he would take the opportunity of pulling down his waistcoat front, which had become disarranged by his energetic working at the bench, and many a time I have come up with the dropped article half blinded by the snuff jerked into my eyes from off his waistcoat front. All the while he was at work, he would be narrating some incident of his past life, or describing the progress of some new and important undertaking, in illustrating which he would use the bit of chalk ready to his hand upon the slate bench before him, which was thus in almost constant use. One of the pleasures he indulged in while he sat at work was music, of which he was very fond, more particularly of melodies and airs which took a lasting hold on his mind. Hence he was never without an assortment of musical boxes, some of which were of a large size. One of these he would set a-going on his library table, which was next to his workshop, and with the door open he was thus enabled to enjoy the music while he sat working at his bench. Intimate friends would frequently call upon him and sit by the hour, but though talking all the while, he never dropped his work, but continued employed on it with as much zeal as if he were only beginning his life. His old friend Sir Samuel Bentham was a frequent caller in this way, as well as Sir Isambard Brunel, while occupied with his Thames Tunnel works, and Mr. Chantry, who was accustomed to consult him about the casting of his bronze statuary. Mr. Barton of the Royal Mint, and Mr. Donkin the engineer, with whom Mr. Barton was associated in ascertaining and devising a correct system of dividing the standard yard, and many others, had like audience of Mr. Maudslay in his little workshop, for friendly converse, for advice, or on affairs of business. It was a special and constant practice with him on a workman's holiday or on a Sunday morning to take a walk through his workshops when all was quiet, and then and there examine the various jobs in hand. On such occasions he carried with him a piece of chalk, with which, in a neat and very legible hand, he would record his remarks in the most pithy and sometimes caustic terms. Any evidence of want of correctness in setting things square or in flat filing, which he held in high esteem, or untidiness in not sweeping down the bench and laying the tools in order, was sure to have a record in the chalk made upon the spot. If it was a mild case, the reproof was recorded in gentle terms, simply to show that the master's eye was on the workman. But where the case deserved hearty approbation or required equally hearty reproof, the words employed were few, but went straight to the mark. These chalk jottings on the bench were held in the highest respect by the workmen themselves, whether they conveyed praise or blame, as they were sure to be deserved, and when the men next assembled, it soon became known all over the shop who had received the honour or otherwise of one of the master's bench memoranda in chalk. The vigilant, the critical, and yet withal the generous eye of the master being over all his workmen, it will readily be understood how Maudslay's works came to be regarded as a first-class school for mechanical engineers. Every one felt that the quality of his workmanship was fully understood, and, if he had the right stuff in him and was determined to advance, that his progress in skill would be thoroughly appreciated. It is scarcely necessary to point out how this feeling, pervading the establishment, must have operated not only in maintaining the quality of the work, but in improving the character of the workman. The results were felt in the increased practical ability of a large number of artisans, some of whom subsequently rose to the highest distinction. Indeed, it may be said that what Oxford and Cambridge are in letters, workshops such as Maudslay and Penn's are in mechanics. Nor can Oxford and Cambridge men be prouder of the connection with their respective colleges than mechanics such as Whitworth, Nasmyth, Roberts, Muir, and Lewis are of their connection with the school of Maudslay. For all these distinguished engineers at one time or another formed part of his working staff, and were trained to the exercise of their special abilities under his own eye. The result has been a development of mechanical ability the like of which perhaps is not to be found in any age or country. Although Mr. Maudslay was an unceasing inventor, he troubled himself very little about patenting his inventions. He considered that the superiority of his tools and the excellence of his work were his surest protection. Yet he had sometimes the annoyance of being threatened with actions by persons who had patented the inventions which he himself had made. He was much beset by inventors, sometimes sadly out at elbows, but always with a boundless fortune looming before them. To such as applied to him for advice in a frank and candid spirit, he did not hesitate to speak freely, and communicate the results of his great experience in the most liberal manner. And to poor and deserving men of this class he was often found as ready to help them with his purse as with his still more valuable advice. He had a singular way of estimating the abilities of those who thus called upon him about their projects. The highest order of man was marked in his own mind at 100 degrees, and by this ideal standard he measured others, setting them down at 90 degrees, 80 degrees, and so on. A very first-rate man he would set down at 95 degrees, but men of this rank were exceedingly rare. After an interview with one of the applicants to him for advice, he would say to his pupil Nasmyth, "Jem, I think that man may be set down at 45 degrees, but he might be worked up to 60 degrees." A common enough way of speaking of the working of a steam engine, but a somewhat novel, though by no means an inexpressive method of estimating the powers of an individual. But while he had much toleration for modest and meritorious inventors, he had a great dislike for secret mongers, schemers of the close, cunning sort, and usually made short work of them. He had an almost equal aversion for what he called the fiddle-faddle inventors, with their omnibus patents, into which they packed every possible thing that their noodles could imagine. "Only once or twice in a century," said he, "does a great inventor appear, and yet here we have a set of fellows each taking out as many patents as will fill a cart, some of them embodying not a single original idea, but including in their specifications all manner of modifications of well-known processes, as well as anticipating the arrangements which may become practicable in the progress of mechanical improvement. Many of these patents he regarded as mere pitfalls to catch the unwary, and he spoke of such inventors as the pests of the profession. The personal appearance of Henry Maudslay was in correspondence with his character. He was of a commanding presence, for he stood full 6 feet 2 inches in height, a massive, portly man. His face was round, full, and lit up with good humour. A fine, large, square forehead, with a grand constructive order, dominated over all, and his bright, keen eye gave energy and life to his countenance. He was thoroughly jolly and good-natured, yet full of force and character. It was a positive delight to hear his cheerful, ringing laugh. He was cordial in manner, and his frankness set everybody at their ease who had occasion to meet him, even for the first time. No one could be more faithful and consistent in his friendships, nor more firm in the hour of adversity. In fine, Henry Maudslay was, as described by his friend Mr. Nasmyth, the very beau ideal of an honest, upright, straightforward, hard-working, intelligent Englishman. A severe cold which he caught on his way home from one of his visits to France was the cause of his death, which occurred on the 14th of February, 1831. The void which his decease caused was long and deeply felt, not only by his family and his large circle of friends, but by his workmen, who admired him for his industrial skill, and loved him because of his invariably manly, generous, and upright conduct towards them. He directed that he should be buried in Woolwich parish churchyard, where a cast-iron tomb, made to his own design, was erected over his remains. He had ever a warm heart for Woolwich, where he had been born and brought up. He often returned to it, sometimes to carry his mother a share of his week's wages while she lived, and afterwards to refresh himself with the sight of the neighbourhood with which he had been so familiar when a boy. He liked its green common, with the soldiers about it, Shooter's Hill, with its outlook over Kent and down the valley of the Thames, the river, busy with shipping, and the royal craft loading and unloading their armaments at the dockyard wharves. He liked the clangour of the Arsenal smithy, where he had first learned his art, and all the busy industry of the place. It was natural, therefore, that being proud of his early connection with Woolwich, he should wish to lie there. And Woolwich, on its part, let us add, has equal reason to be proud of Henry Maudslay. End of chapter 12. Chapter 13, Part 1 of Industrial Biography, Ironworkers and Toolmakers by Samuel Smiles. This LibriVox recording is in the public domain. Recording by Clive Catterall. Joseph Clement. It is almost impossible to overestimate the importance of these inventions. The Greeks would have elevated their authors among the gods, nor will the enlightened judgment of modern times deny them the place among their fellow men which is so undeniably their due. Edinburgh Review. That skill in mechanical contrivance is a matter of education and training as well as of inborn faculty is clear from the fact of so many of our distinguished mechanics undergoing the same kind of practical discipline, and perhaps still more so from the circumstance of so many of them passing through the same workshops. Thus Maudslay and Clement were trained in the workshops of Bramah, and Roberts, Whitworth, Nasmyth, and others were trained in those of Maudslay. Joseph Clement was born at Great Ashby in Westmoreland in the year 1779. His father was a hand-loom weaver, and a man of remarkable culture considering his humble station in life. He was an ardent student of natural history, and possessed a much more complete knowledge of several sub-branches of that science than was to have been looked for in a common working man. One of the departments which he specially studied was entomology. In his leisure hours he was accustomed to traverse the country searching the hedge-bottoms for beetles and other insects, of which he formed a remarkably complete collection, and the capture of a rare specimen was quite an event in his life. In order more deliberately to study the habits of the bee tribe, he had a number of hives constructed for the purpose of enabling him to watch their proceedings without leaving his work, and the pursuit was a source of the greatest pleasure to him. He was a lover of all dumb creatures. His cottage was haunted by birds which flew in and out at his door, and some of them became so tame as to hop up to him and feed out of his hand. Old Clement was also a bit of a mechanic, and such of his leisure moments as he did not devote to insect hunting were employed in working a lathe of his own construction, which he used to turn his bobbins and also various kinds of amateur mechanics. His boy Joseph, like other poor men's sons, was early set to work. He received very little education, and learnt only the merest rudiments of reading and writing at the village school. The rest of his education he gave to himself as he grew older. His father needed his help at the loom, where he worked with him for some years, but as hand-loom weaving was gradually being driven out by improved mechanism, the father prudently resolved to put his son to a better trade. They have a saying in Cumberland that when the bairns reach a certain age, they are thrown on the house rig, and those who stick on are made thatchers of, while those who fall off are sent to St. Bees to be made parsons of. Joseph must have been one of those that stuck on. At all events, his father decided to make him a thatcher, afterwards a slater, and he worked at that trade for 5 years between 18 and 23. The son, like the father, had a strong liking for mechanics, and as the slating trade did not keep him in regular employment, especially in winter time, he had plenty of opportunity for following the bent of his inclinations. He made a friend of the village blacksmith, whose smithy he was accustomed to frequent, and there he learned to work at the forge, to handle the hammer and file, and in a short time to shoe horses with considerable expertness. A cousin of his, named Farrer, a clock and watchmaker by trade, having returned to the village from London, brought with him some books on mechanics which he lent to Joseph to read, and they kindled in him an ardent desire to be a mechanic instead of a slater. He nevertheless continued to maintain himself by the latter trade for some time longer, until his skill had grown, and by way of cultivating it he determined, with the aid of his friend the village blacksmith, to make a turning lathe. The two set to work, and the result was the production of an article in every way superior to that made by Clement's father, which was accordingly displaced to make room for the new machine. It was found to work very satisfactorily, and by its means Joseph proceeded to turn fifes, flutes, clarinets, and hautboys, for to his other accomplishments he joined that of music, and could play upon the instruments that he made. One of his most ambitious efforts was the making of a pair of Northumberland bagpipes, which he finished to his satisfaction and performed upon to the great delight of the villagers. To assist his father in his entomological studies, he even contrived, with the aid of the descriptions given in the books borrowed from his cousin the watchmaker, to make for him a microscope, from which he proceeded to make a reflecting telescope, which proved a very good instrument. At this early period, 1804, he also seems to have directed his attention to screw-making, a branch of mechanics in which he afterwards became famous, and he proceeded to make a pair of very satisfactory die-stocks, though it is said that he had not before seen or even heard of such a contrivance for making screws. So clever a workman was not likely to remain long a village slater. Although the ingenious pieces of work which he turned out by his lathe did not bring him in much money, he liked the occupation so much better than slating that he was gradually giving up that trade. His father urged him to stick to slating as a safe thing, but his own mind was in favour of following his instincts to be a mechanic, and at length he determined to leave his village and seek work in a new line. He succeeded in finding employment in a small factory at Kirkby Stephen, a town some 13 miles from Great Ashby, where he worked at making power looms. From an old statement of account against his employer which we've seen, in his own handwriting, dated the 6th of September 1805, it appears that his earnings at such work as fitting the first set of iron looms, fitting up shuttles, and making models, were 3 shillings 6pence a day, and he must, during the same time, have lived with his employer, who charged him a set-off 14 weeks' board at 8 shillings per week. He afterwards seems to have worked at piecework in partnership with one Andrew Gamble, supplying the materials as well as the workmanship for the looms and shuttles. His employer, Mr. George Dickinson, also seems to have bought his reflecting telescope from him for the sum of £12. From Kirkby Stephen, Clement removed to Carlisle, where he was employed by Foster and Sons during the next 2 years at the same description of work, and he conducted himself, according to their certificate on his leaving their employment to proceed to Glasgow in 1807, with great sobriety and industry, entirely to their satisfaction. While working at Glasgow as a turner, he took lessons in drawing from Peter Nicholson, the well-known writer on carpentry, a highly ingenious man. Nicholson happened to call at the shop at which Clement worked in order to make a drawing of a power loom, and Clement's expressions of admiration at his expertness were so enthusiastic that Nicholson, pleased with the youth's praise, asked if he could be of service to him in any way. Emboldened by the offer, Clement requested, as the greatest favour he could confer upon him, to have the loan of the drawing he had just made, in order that he might copy it. The request was at once complied with, and Clement, though very poor at the time, and scarcely able to buy candles for the long winter evenings, sat up late every night until he had finished it. Though the first drawing he had ever made, he handed it back to Nicholson instead of the original, and at first the draftsman did not recognise that the drawing was not his own. When Clement told him that it was only the copy, Nicholson's brief but emphatic praise was, "Young man, you'll do." Proud to have such a pupil, Nicholson generously offered to give him gratuitous lessons in drawing, which he thankfully accepted, and Clement, working at nights with great ardour, soon made rapid progress and became an expert draftsman. Trade being very slack in Glasgow at the time, Clement, after about a year's stay in the place, accepted a situation with Messrs. Lees, Masson and Company, of Aberdeen, with whom he began at £1.50 a week, from which he gradually rose to 2 guineas and ultimately 3 guineas. His principal work consisted in designing and making power looms for his employers, and fitting them up in different parts of the country. He continued to devote himself to the study of practical mechanics, and made many improvements in the tools with which he worked. While at Glasgow he made an improved pair of die stocks for screws, and at Aberdeen he made a turning lathe with sliding mandrel and guide screws for cutting screws, furnished also with the means of correcting guide screws. In the same machine he introduced a small slide rest, into which he fixed the tool for cutting the screws, having never before seen a slide rest, though it is very probable he may have heard of what Maudslay had already done in the same direction. Clement continued during this period of his life an industrious self-cultivator, occupying most of his spare hours in mechanical and landscape drawing, and in various studies. Among the papers left behind him we find a ticket to a course of instruction on natural philosophy, given by Professor Copeland at the Marischal College at Aberdeen, which Clement attended in the session of 1812-13. And we do not doubt that our mechanic was among the most diligent of his pupils. Towards the end of 1813, after saving about £100 out of his wages, Clement resolved to proceed to London for the purpose of improving himself in his trade, and pushing his way in the world. The coach by which he travelled set him down at Snow Hill, Holborn, and his first thought was of finding work. He had no friend in town to consult on the matter, so he made inquiry of the coach guard whether he knew of any person in the mechanical line in that neighbourhood. The guard said, yes, there was Alexander Galloway's show shop just round the corner, and he employed a large number of hands. Running round the corner, Clement looked in at Galloway's window, through which he saw some lathes and other articles used in machine shops. Next morning he called upon the owner of the shop to ask employment. "What can you do?" asked Galloway. "I can work at the forge," said Clement. "Anything else?" "I can turn." "What else?" "I can draw." "What?" said Galloway. "Can you draw? Then I will engage you." A man who could draw or work to a drawing in those days was regarded as a superior sort of mechanic. Though Galloway was one of the leading tradesmen of his time, and had excellent opportunities for advancement, he missed them all. As Clement afterwards said of him, he was only a mouthing common council man, the height of whose ambition was to be an alderman. And like most corporation celebrities, he held a low rank in his own business. He very rarely went into his workshops to superintend or direct his workmen, leaving this to his foreman, a sufficient indication of the cause of his failure as a mechanic. On entering Galloway's shop, Clement was first employed in working at the lathe, but finding the tools so bad that it was impossible to execute satisfactory work with them, he at once went to the forge and began making a new set of tools for himself. The other men, to whom such a proceeding was entirely new, came round him to observe his operations, and they were much struck with his manual dexterity. The tools made, he proceeded to use them, displaying what seemed to the other workmen an unusual degree of energy and intelligence, and some of the old hands did not hesitate already to pronounce Clement to be the best mechanic in the shop. When Saturday night came round, the other men were curious to know what wages Galloway would allow the new hand, and when he had been paid, they asked him. "A guinea," was the reply. "A guinea? Why, you are worth 2 if you're worth a shilling," said an old man who came out of the rank, an excellent mechanic who, though comparatively worthless through his devotion to drink, knew Clement's money value to his employer better than any there. And he added, "Wait for a week or two, and if you're not better paid than this, I can tell you of a master who will give you a fairer wage." Several Saturdays came round, but no advance was made on a guinea a week, and then the old workman recommended Clement to offer himself to Bramah at Pimlico, who was always on the lookout for first-rate mechanics. Clement acted on the advice, and took with him some of his drawings, at sight of which Bramah immediately engaged him for a month, and at the end of that time he had given so much satisfaction that it was agreed he should continue for 3 months longer at 2 guineas a week. Clement was placed in charge of the tools of the shop, and he showed himself so apt at introducing improvements in them, as well as in organising the work with a view to dispatch and economy, that at the end of the term Bramah made him a handsome present, adding, "If I had secured your services 5 years since, I would now have been a richer man by many thousands of pounds." A formal agreement for a term of 5 years was then entered into between Bramah and Clement, dated the 1st of April 1814, by which the latter undertook to fill the office of chief draftsman and superintendent at the Pimlico works, in consideration of a salary of 3 guineas a week, with an advance of 4 shillings a week in each succeeding year of the engagement. This arrangement proved of mutual advantage to both. Clement devoted himself with increased zeal to the improvement of the mechanical arrangements in the concern, exhibiting his ingenuity in many ways, and taking a genuine pride in upholding the character of his master for turning out first-class work. On the death of Bramah, his sons returned from college, and entered into possession of the business. They found Clement the ruling mind there, and grew jealous of him to such an extent that his situation became uncomfortable, and by mutual consent he was allowed to leave before the expiry of his term of agreement. He had no difficulty in finding employment, and was at once taken on as chief draftsman at Maudslay and Fields, where he was of much assistance in proportioning the early marine engines, for the manufacture of which that firm were becoming celebrated. After a short time he became desirous of beginning business on his own account as a mechanical engineer. He was encouraged to do this by the Duke of Northumberland, who, being a great lover of mechanics and himself a capital turner, used often to visit Maudslay's, and thus became acquainted with Clement, whose expertness as a draftsman and mechanic he greatly admired. Being a man of frugal and sober habits, always keeping his expenditure very considerably within his income, Clement had been enabled to accumulate about £500, which he thought would be enough for his purpose, and accordingly he proceeded, in 1817, to take a small workshop in Prospect Place, Newington Butts, where he began business as a mechanical draftsman and manufacturer of small machinery requiring first-class workmanship. From the time when he took his first gratuitous lessons in drawing from Peter Nicholson at Glasgow in 1807, he had been steadily improving in this art, the knowledge of which is indispensable to whoever aspires to eminence as a mechanical engineer, until, by general consent, Clement was confessed to stand unrivalled as a draftsman. Some of the very best drawings contained in the Transactions of the Society of Arts from the year 1817 downwards, especially those requiring the delineation of any unusually elaborate piece of machinery, proceeded from the hand of Clement. In some of these he reached a degree of truth in mechanical perspective which has never been surpassed. To facilitate his labours he invented an extremely ingenious instrument by means of which ellipses of all proportions, as well as circles and right lines, might be geometrically drawn on paper or on copper. He took his idea of this instrument from the trammel used by carpenters for drawing imperfect ellipses, and when he had succeeded in avoiding the crossing of the points, he proceeded to invent the straight line motion. For this invention the Society of Arts awarded him their gold medal in 1818. Some years later he submitted to the same society his invention of a stand for drawings of large size. He had experienced considerable difficulty in making such drawings, and with his accustomed readiness to overcome obstacles, he forthwith set to work and brought out his new drawing table. As with many other original-minded mechanics, invention became a habit with him, and by study and labour he rarely failed in attaining the object which he had bent his mind upon accomplishing. Indeed, nothing pleased him better than to have what he called a tough job, as it stimulated his inventive faculty, in the exercise of which he took the highest pleasure. Hence mechanical schemers of all kinds were accustomed to resort to Clement for help when they had found an idea which they desired to embody in a machine. If there was any value in their idea, none could be more ready than he to recognise its merit, and to work it into shape. But if worthless, he spoke out his mind at once, dissuading the projector from wasting upon it further labour and expense. One of the important branches of practical mechanics to which Clement continued through his life to devote himself was the improvement of self-acting tools, more especially of the slide lathe. He introduced various improvements in its construction and arrangement, until in his hands it became as nearly perfect as it was possible to be. In 1818 he furnished the lathe with a slide rest 22 inches long for the purpose of cutting screws, provided with the means of self-correction, and some years later, in 1827, the Society of Arts awarded him their gold Isis medal for his improved turning lathe, which embodied many ingenious contrivances calculated to increase its precision and accuracy in large surface turning. The beautiful arrangements embodied in Mr. Clement's improved lathe can with difficulty be described in words, but its ingenuity may be inferred from a brief statement of the defects which it was intended to remedy, and which it successfully overcame. When the mandrel of a lathe, having a metal plate fixed to it, turns round with a uniform motion, and the slide rest which carries the cutter is moving from the circumference of the work to the centre, it will be obvious that the quantity of metal passing over the edge of the cutter at each revolution, and therefore at equal intervals of time, is continually diminishing, in exact proportion to the spiral line described by the cutter on the face of the work. But in turning metal plates it is found very inexpedient to increase the speed of the work beyond a certain quantity, for when this happens, and the tool passes the work with too great a velocity, it heats and softens, and is ground away, the edge of the cutter becomes dull, and the surface of the plate is indented and burnished instead of being turned. Hence loss of time on the part of the workman and diminished work on the part of the tool results, which, considering the wages of the one and the capital expended on the construction of the other, are of no small importance. For the prime objects of all improvements of tools are economy of time and economy of capital, to minimize labour and cost and maximize the result. The defect to which we have referred was almost the only remaining imperfection in the lathe, and Mr. Clement overcame it by making the machine self-regulating, so that whatever might be the situation of the cutter, equal quantities of metal should pass over it in equal times, the speed at the centre not exceeding that suited to the work at the circumference, while the workman was enabled to convert the varying rate of the mandrel into a uniform one whenever he chose. Thus the expedients of wheels, riggers, and drums of different diameters, by which it had been endeavoured to alter the speed of the lathe mandrill according to the hardness of the metal and the diameter of the thing to be turned, were effectually disposed of. These, though answering very well when cylinders of equal diameter had to be bored and a uniform motion was all that was required, were found very inefficient when a plain surface had to be turned. And it was in such cases that Mr. Clement's lathe was found so valuable. By its means, surfaces of unrivalled correctness were produced, and the slide lathe so improved became recognised and adopted as the most accurate and extensively applicable of all machine tools. End of Chapter 13, Part 1. Chapter 13, Part 2 of Industrial Biography, Ironworkers and Toolmakers by Samuel Smiles. This LibriVox recording is in the public domain. Recording by Clive Catterall. Joseph Clement, Part 2. The year after Mr. Clement bought out his improved turning lathe, he added to it his self-adjusting double-driving centre chuck, for which the Society of Arts awarded him their silver medal in 1828. In introducing this invention to the notice of the Society, Mr. Clement said, "Although I have been in the habit of turning and making turning lathes and other machinery for upwards of 35 years, and have examined the best turning lathes in the principal manufactories throughout Great Britain, I find it universally regretted by all practical men that they cannot turn anything perfectly true between the centres of the lathe." It was found by experience that there was a degree of eccentricity, and consequently of imperfection, in the figure of any long cylinder turned while suspended between the centres of the lathe and made to revolve by the action of a single driver. Under such circumstances, the pressure of the tool tended to force the work out of the right line, and to distribute the strain between the driver and the adjacent centre, so that one end of the cylinder became eccentric with respect to the other. By Mr. Clement's invention of the two-armed driver, which was self-adjusting, the strain was taken from the centre and divided between the two arms, which being equidistant from the centre, effectually corrected all eccentricity in the work. This invention was found of great importance in ensuring the true turning of large machinery, which before had been found a matter of considerable difficulty. In the same year, 1828, Mr. Clement began the making of fluted taps and dies, and he established a mechanical practice with reference to the pitch of the screw, which proved of the greatest importance in the economics of manufacture. Before his time, each mechanical engineer adopted a thread of his own, so that when a piece of work came under repair, the screw hob had usually to be drilled out, and a new thread was introduced, according to the usage which prevailed in the shop in which the work was executed. Mr. Clement saw a great waste of labour in this practice, and he promulgated the idea that every screw of a particular length ought to be furnished with its appointed number of threads of a settled pitch. Taking the inch as the basis of his calculations, he determined the number of threads in each case, and the practice thus initiated by him, recommended as it was by convenience and economy, was very shortly adopted throughout the trade. It may be mentioned that one of Clement's ablest journeymen, Mr. Whitworth, has since his time been mainly instrumental in establishing the settled practice, and Whitworth's thread, initiated by Clement, has become recognised throughout the mechanical world. To carry out his idea, Clement invented his screw-engine lathe, with gearing, mandrill, and sliding table wheelwork, by means of which he first cut the inside screw tools from the left-handed hobs, the reverse mode having before been adopted, while in shaping machines he was the first to use the revolving cutter attached to the slide rest. Then, in 1828, he fluted the taps for the first time with a revolving cutter, other makers having up to that time only notched them. Among his other inventions in screws may be mentioned his headless tap, which, according to Mr. Nasmyth, is so valuable an invention that, if he had done nothing else, it ought to immortalize him among mechanics. It passed right through the hole to be tapped, and was thus enabled to do the duty of 3 ordinary screws. By these improvements much greater precision was secured in the manufacture of tools and machinery, accompanied by a greatly reduced cost of production, the results of which are felt to this day. Another of Mr. Clement's ingenious inventions was his planing machine, by means of which metal plates of large dimensions were planed with perfect truth and finished with beautiful accuracy. There is perhaps scarcely a machine about which there has been more controversy than this, and we do not pretend to be able to determine the respective merits of the many able mechanics who have had a hand in its invention. It is exceedingly probable that others beside Clement worked out the problem in their own way by independent methods, and this is confirmed by the circumstance that, though the results achieved by the respective inventors were the same, the methods employed by them were in many respects different. As regards Clement, we find that previous to the year 1820 he had a machine in regular use for planing the triangular bars of lathes and the sides of weaving looms. This instrument was found so useful and so economical in its working that Clement proceeded to elaborate a planing machine of a more complete kind, which he finished and set to work in the year 1825. He prepared no model of it, but made it directly from the working drawings, and it was so nicely constructed that when put together it went without a hitch, and has continued steadily working for more than 30 years down to the present day. Clement took out no patent for his invention, relying for protection mainly on his own and his workmen's skill in using it. We therefore find no specification of his machine at the Patent Office, as in the case of most other capital inventions, but a very complete account of it is to be found in the Transactions of the Society of Arts for 1832, as described by Mr. Varley. The practical value of the planing machine induced the Society to apply to Mr. Clement for liberty to publish a full description of it, and Mr. Varley's paper was the result. It may be briefly stated that this engineer's plane differs greatly from the carpenter's plane, the cutter of which is only allowed to project so far as to admit of a thin shaving to be sliced off, the plane working flat in proportion to the width of the tool, and its length and straightness preventing the cutter from descending in any hollows in the wood. The engineer's plane more resembles the turning lathe, of which, indeed, it is but a modification, working up on the same principle on flat surfaces. The tools or cutters in Clement's machine were similar to those used in the lathe, varying in like manner, but performing their work in right lines, the tool being stationary and the work moving under it, the tool only travelling when making lateral cuts. To save time, 2 cutters were mounted, one to cut while the work going, and the other while returning, both being so arranged and held as to be presented to the work in the firmest manner, with the least possible friction. The bed of the machine on which the work was laid passed under the cutters on perfectly true rollers or wheels, lodged and held in their bearings as accurately as the best mandrel could be, and having set screws acting against their ends totally preventing all end motion. The machine was bedded on a massive and solid foundation of masonry in heavy blocks, the support at all points being so complete as effectually to destroy all tendency to vibration, with the object of securing full, round, and quiet cuts. The rollers on which the planing machine travelled were so true that Clement himself used to say of them, if you were to put a paper shaving under one of the rollers, it would at once stop all the rest. Nor was this any exaggeration, the entire mechanism, notwithstanding its great size, being as true and as accurate as that of a watch. By an ingenious adaptation of the apparatus, which will also be found described in the Society of Arts paper, the planing machine might be fitted with a lathe bed, either to hold 2 centres or a head with a suitable mandrel. When so fitted, the machine was enabled to do the work of a turning lathe, though in a different way, cutting cylinders or cones in their longitudinal direction perfectly straight, as well as solids or prisms of any angle, either by the longitudinal or lateral motion of the cutter, whilst by making the work revolve it might be turned as in any other lathe. This ingenious machine, as contrived by Mr. Clement, therefore represented a complete union of the turning lathe with the planing machine and dividing engine, by which turning of the most complicated kind might readily be executed. For 10 years after it was set in motion, Clement's was the only machine of the sort available for planing large work, and being consequently very much in request, it was often kept going night and day, the earnings by the planing machine alone during that time forming the principal income of its inventor. As it took in a piece of work 6 feet square, and by his charge for planing was 3 halfpence the square inch, or 18 shillings the square foot, he could thus earn by his machine alone some £10 for every day's work of 12 hours. We may add that since planing machines in various forms have become common in mechanical workshops, the cost of planing does not amount to more than 3 halfpence the square foot. The excellence of Mr. Clement's tools, and his well-known skill in designing and executing work requiring unusual accuracy and finish, led to his being employed by Mr. Babbage to make his celebrated calculating or difference engine. The contrivance of a machine that should work out complicated sums in arithmetic with perfect precision was, as may be readily imagined, one of the most difficult feats of the mechanical intellect. To do this was in an especial sense to stamp matter with the impress of mind, and render it subservient to the highest thinking faculty. Attempts had been made at an early period to perform arithmetical calculations by mechanical aids more rapidly and precisely than it was possible to do by the operations of the individual mind. The preparation of arithmetical tables of high numbers involved a vast deal of labour, and even with the greatest care, errors were unavoidable and numerous. Thus, in a multiplication table prepared by a man so eminent as Dr. Hutton for the Board of Longitude, no fewer than 40 errors were discovered in a single page taken at random. In the tables of the Nautical Almanac, where the greatest possible precision was desirable and necessary, more than 500 errors were detected by one person, and the tables of the Board of Longitude were found equally incorrect. But such errors were impossible to be avoided so long as the ordinary modes of calculating, transcribing, and printing continued in use. The earliest and simplest form of calculating apparatus was that employed by the schoolboys of ancient Greece, called the abacus, consisting of a smooth board with a narrow rim, on which they were taught to compute by means of progressive rows of pebbles, bits of bone or ivory, or pieces of silver coin, used as counters. The same board, strewn over with sand, was used for teaching the rudiments of writing and the principles of geometry. The Romans subsequently adopted the abacus, dividing it by means of perpendicular lines or bars, and from the description of calculus, which they gave to each pebble or counter employed on the board, we have derived our English word to calculate. The same instrument continued to be employed during the Middle Ages, and the table used by the English Court of Exchequer was but a modified form of the Greek abacus, the checkered lines across it giving the designation to the court, which still survives. Tallies, from the French word tailler, to cut, were another of the mechanical methods employed to record computations, though in a very rude way. Step by step, improvements were made, the most important being that invented by Napier of Merchiston, the inventor of logarithms, commonly called Napier's bones, consisting of a number of rods divided into 10 equal squares and numbered, so that the whole, when placed together, formed the common multiplication table. By these means various operations in multiplication and division were performed. Sir Samuel Morland, Gunter, and Lamb introduced other contrivances applicable to trigonometry, Gunter's scale being still in common use. The calculating machines of Gersten and Pascal were of a different kind, working out arithmetical calculations by means of trains of wheels and other arrangements, and that contrived by Lord Stanhope for the purpose of verifying his calculations with respect to the national debt was of like character. But none of these will bear for a moment to be compared with a machine designed by Mr. Babbage, for performing arithmetical calculations and mathematical analyses, as well as for recording the calculations when made, thereby getting rid entirely of individual error in the operations of calculation, transcription, and printing. The French government, in their desire to promote the extension of the decimal system, had ordered the construction of logarithmical tables of vast extent. But the great labour and expense involved in the undertaking prevented the design from being carried out. It was reserved for Mr. Babbage to develop the idea by means of a machine which he called the difference engine. This machine is of so complicated a character that it would be impossible for us to give any intelligible description of it in words. Although Dr. Lardner was unrivalled in the art of describing mechanism, he occupied 25 pages of the Edinburgh Review, volume 59, in endeavouring to describe its action, and there were several features in it which he gave up as hopeless. Some parts of the apparatus and modes of action are indeed extraordinary, and perhaps none more so than that for ensuring accuracy in the calculated results, the machine actually correcting itself, and rubbing itself back into accuracy when the disposition to err occurs by the friction of adjacent machinery. When an error is made, the wheels become locked and refuse to proceed. Thus the machine must go rightly or not at all, an arrangement as nearly resembling volition as anything that brass and steel are likely to accomplish. This intricate subject was taken up by Mr. Babbage in 1821, when he undertook to superintend for the British government the construction of a machine for calculating and printing mathematical and astronomical tables. The model first constructed to illustrate the nature of his invention produced figures at the rate of 44 a minute. In 1832 the Royal Society was requested to report upon the invention, and after full inquiry the committee recommended it as one deserving of public encouragement. A sum of £1,500 was then placed at Mr. Babbage's disposal by the Lords of the Treasury for the purposes of enabling him to perfect his invention. It was at this time that he engaged Mr. Clement as draftsman and mechanic to embody his ideas in a working machine. Numerous tools were expressly contrived by the latter for executing the several parts, and workmen were specially educated for the purpose of using them. Some idea of the elaborate character of the drawings may be formed from the fact that those required for the calculating machinery alone, not to mention the printing machinery, which was almost equally elaborate, covered not less than 400 square feet of surface. The cost of executing the calculating machine was of course very great, and the progress of the work was necessarily slow. The consequence was that the government first became impatient, and then began to grumble at the expense. At the end of 7 years the engineer's bills alone were found to amount to nearly £7,200, and Mr. Babbage's costs out of pocket to £7,000 more. In order to make more satisfactory progress, it was determined to remove the works to the neighbourhood of Mr. Babbage's own residence. But as Clement's claims for conducting the operations in the new premises were thought exorbitant, and as he himself considered that the work did not yield him the average profit of ordinary employment in his own trade, he eventually withdrew from the enterprise, taking with him the tools which he had constructed for executing the machine. The government also shortly after withdrew from it, and from that time the scheme was suspended, the calculating engine remaining a beautiful but unfinished fragment of a great work. Though originally intended to go as far as 20 figures, it was only completed to the extent of being capable of calculating to the depth of 5 figures and 2 orders of difference, and only a small part of the proposed printing machinery was ever made. The engine was placed in the Museum of King's College in 1843, enclosed in a glass case, until the year 1862, when it was removed for a time to the Great Exhibition, where it formed perhaps the most remarkable and beautifully executed piece of mechanism, the combined result of intellectual and mechanical contrivance, in the entire collection. Clement was on various other occasions invited to undertake work requiring extra skill, which other mechanics were unwilling or unable to execute. He was thus always full of employment, never being under the necessity of canvassing for customers. He was almost constantly in his workshop, in which he took great pride. His dwelling was over the office in the yard, and it was with difficulty he could be induced to leave the premises.
On one occasion, Mr. Brunel of the Great Western Railway called upon him to ask if he could supply him with a superior steam whistle for his locomotives, the whistles which they were using giving forth very little sound. Clement examined the specimen brought by Brunel, and pronounced it to be mere tallow chandler's work. He undertook to supply the proper article, and after his usual fashion he proceeded to contrive a machine or tool for the express purpose of making steam whistles. They were made and supplied, and when mounted on the locomotive the effect was indeed screaming. They were heard miles off, and Brunel, delighted, ordered 100. But when the bill came in, it was found that the charge made for them was very high, as much as £40 the set. The company demurred at the price, Brunel declaring it to be 6 times more than the price they had before been paying. "That may be," rejoined Clement, "but mine are more than 6 times better. You ordered a first-rate article, and you must be content to pay for it." The matter was referred to an arbitrator, who awarded the full sum claimed. Mr. Weld mentions a similar case of an order which Clement received from America to make a large screw of given dimensions in the best possible manner, and he accordingly proceeded to make one with the greatest mathematical accuracy. But his bill amounted to some hundreds of pounds, which completely staggered the American, who did not calculate on having to pay more than £20 at the utmost for the screw. The matter was, however, referred to arbitrators, who gave the decision, as in the former case, in favour of the mechanic. One of the last works which Clement executed as a matter of pleasure was the building of an organ for his own use. It will be remembered that when working as a slater at Great Ashby he had made flutes and clarinets, and now in his old age he determined to try his skill at making an organ, in his opinion the king of musical instruments. The building of it became his hobby, and his greatest delight was in superintending its progress. It cost him about £2,000 in labour alone, but he lived to finish it, and we have been informed that it was pronounced a very excellent instrument. Clement was a heavy-browed man, without any polish of manner or speech, for to the last he continued to use his strong Westmoreland dialect. He was not educated in a literary sense, for he had read but little, and could write with difficulty. He was eminently a mechanic, and had achieved his exquisite skill by observation, experience, and reflection. His head was a complete repertory of inventions, on which he was constantly drawing for the improvement of mechanical practice. Though he had never more than 30 workmen in his factory, they were all of the first class, and the example which Clement set before them of extreme carefulness and accuracy in execution rendered his shop one of the best schools of its time for the training of thoroughly accomplished mechanics. Mr. Clement died in 1844, in his 65th year, after which his works were carried on by Mr. Wilkinson, one of his nephews, and his planing machine still continues in useful work. End of chapter 13. Chapter 14 of Industrial Biography, Ironworkers and Toolmakers, by Samuel Smiles. This LibriVox recording is in the public domain. Recording by Clive Catterall. Fox of Derby, Murray of Leeds, Roberts and Whitworth of Manchester. Founders and senators of states and cities, lawgivers, extirpers or tyrants, fathers of the people, and other eminent persons in civil government were honoured, but with titles of worthies or demigods, whereas such as were inventors and authors of new arts, endowments, and commodities towards man's life were ever consecrated amongst the gods themselves. Bacon, Advancement of Learning. While such were the advances made in the arts of tool-making and engine construction through the labours of Bramah, Maudslay, and Clement, there were other mechanics of almost equal eminence who flourished about the same time and subsequently in several of the northern manufacturing towns. Among these may be mentioned James Fox of Derby, Matthew Murray and Peter Fairbairn of Leeds, Richard Roberts, Joseph Whitworth, James Nasmyth, and William Fairbairn of Manchester, to all of whom the manufacturing industry of Great Britain stands in the highest degree indebted. James Fox, the founder of the Derby firm of mechanical engineers, was originally a butler in the service of Rev. Thomas Gisborne of Foxhall Lodge, Staffordshire. Though a situation of this kind might not seem by any means favourable for the display of mechanical ability, yet the butler's instinct for handicraft was so strong that it could not be repressed, and his master not only encouraged him in the handling of tools in his leisure hours, but had so genuine an admiration of his skill, as well as his excellent qualities of character, that he eventually furnished him with the means of beginning business on his own account. The growth and extension of the cotton, silk, and lace trades in the neighbourhood of Derby furnished Fox with sufficient opportunities for the exercise of his mechanical skills, and he soon found ample scope for its employment. His lace machinery became celebrated, and he supplied it largely to the neighbouring town of Nottingham. He also obtained considerable employment from the great firms of Arkwright and Strutt, the founders of the modern cotton manufacture. Mr. Fox also became celebrated for his lathes, which were of excellent quality, still maintaining their high reputation. And besides making largely for the supply of the home demand, he exported much machinery abroad to France, Russia, and the Mauritius. The present Messrs. Fox of Derby, who continue to carry on the business of the firm, claim for their grandfather, its founder, that he made the first planing machine in 1814, and they add that the original article continued in use until quite recently. We have been furnished by Samuel Hall, formerly a workman at the Messrs. Fox's, with the following description of the machine. It was essentially the same in principle as the planing machine now in general use, although differing in detail. It had a self-acting ratchet motion for moving the slide of a compound slide rest, and a self-acting reversing tackle, consisting of 3 bevel wheels, one a stud, one loose on the driving shaft, and another on a socket, with a pinion on the opposite end of the driving shaft running on the socket. The other end was the place for the driving pulley. A clutch box was placed between the 2 opposite wheels, which was made to slide on a feather, so that by means of another shaft containing levers and a tumbling ball, the box, on reversing, was carried from one bevelled wheel to the opposite one. The same James Fox is also said, at a very early period, to have invented a screw-cutting machine, an engine for accurately dividing and cutting teeth of wheels, and a self-acting lathe. But the evidence as to the dates at which these several inventions are said to have been made is so conflicting that it is impossible to decide with whom the merit of making them really exists. The same idea is found floating at the same time in many minds, the like necessity pressing upon all, and the process of invention takes place in like manner. Hence the contemporaneousness of so many inventions, and the disputes that arise respecting them, as described in the previous chapter. There are still other claimants for the merit of having invented the planing machine, among whom may be mentioned more particularly Matthew Murray of Leeds and Richard Roberts of Manchester. We are informed by Mr. March, the present Mayor of Leeds, head of the celebrated tool manufacturing firm of that town, that when he first went to work at Matthew Murray's in 1814, a planing machine of his invention was used to plane the circular part or back of the D-valve, which he had by that time introduced in the steam engine. Mr. March says, "I recollect it very distinctly, and even the sort of framing on which it stood." The machine was not patented, and like many inventions in those days, it was kept as much a secret as possible, being locked up in a small room by itself, to which the ordinary workman could not obtain access. The year in which I remember it being in use was, so far as I am aware, long before any planing machine of a similar kind had been invented. Matthew Murray was born at Stockton-on-Tees in the year 1763. His parents were of the working class, and Matthew, like the other members of his family, was brought up with the ordinary career of labourer before him. When of due age, his father apprenticed him to the trade of a blacksmith, in which he very soon acquired considerable expertness. He married before his term had expired, after which, trade being slack at Stockton, he found it necessary to look for work elsewhere. Leaving his wife behind him, he set out for Leeds with his bundle on his back, and, after a long journey on foot, he reached that town with not enough money left in his pocket to pay for a bed at the Bay Horse Inn where he had put up. But telling the landlord that he expected work at Marshall's, and seeming to be a respectable young man, the landlord trusted him, and he was so fortunate as to obtain the job which he sought at Mr. Marshall's, who was then beginning the manufacture of flax, for which the firm has since become so famous. Mr. Marshall was at that time engaged in improving the method of manufacture, and the young blacksmith was so fortunate, or rather so dexterous, as to be able to suggest several improvements in the machinery which secured the approval of his employer, who made him a present of £20, and very shortly promoted him to be the first mechanic in the workshop. On this stroke of good fortune, Murray took a house in the neighbouring village of Beeston, sent to Stockton for his wife, who speedily joined him, and he now felt himself fairly started in the world. He remained with Mr. Marshall for about 12 years, during which he introduced numerous improvements in the machinery for spinning flax, and obtained the reputation for being a first-rate mechanic. This induced Mr. James Fenton and Mr. David Wood to offer to join him in the establishment of an engineering and machine-making factory at Leeds, which he agreed to, and operations were commenced at Holbeck in the year 1795. As Mr. Murray had obtained considerable practical knowledge of the steam engine while working at Mr. Marshall's, he took principal charge of the engine-building department, while his partner, Wood, directed the machine-making. In the branch of engine-building, Mr. Murray very shortly established a high reputation, treading close upon the heels of Boulton and Watt, so close indeed that the firm became very jealous of him, and purchased a large piece of ground close to his works with the object of preventing their extension. His additions to the steam engine were of great practical value, one of which, the self-acting apparatus attached to the boiler for the purpose of regulating the intensity of the fire under it, and consequently of the production of steam, is still in general use. This was invented by him as early as 1799. He also subsequently invented the D-slide valve, or at least greatly improved it, while he added to the power of the air pump and gave a new arrangement to the other parts, with a view to the simplification of the powers of the engine. To make the D-valve work efficiently, it was found necessary to form two perfectly plane surfaces, to produce which he invented his planing machine. He was also the first to adopt the practice of placing the piston in a horizontal position in the common condensing engine. Among his other modifications to the steam engine was his improvement of the locomotive, as invented by Trevithick, and it ought to be remembered to his honour that he made the first locomotive that regularly worked upon any railway. This was the engine erected by him for Blenkinsop, to work the Middleton Colliery Railway near Leeds, on which it began to run in 1812, and continued in regular use for many years. In this engine he introduced the double cylinder, Trevithick's engine being provided with only one cylinder, the defects of which were supplemented by the addition of a flywheel to carry the crank over the dead points. But Matthew Murray's most important inventions, considered in their effects on manufacturing industry, were those connected with the machinery for heckling and spinning flax, which he greatly improved. His heckling machine obtained for him the prize of the Gold Medal of the Society of Arts, and this, as well as his machine for wet flax spinning by means of sponge weights, proved to the greatest practical value. At the time when these inventions were made, the flax trade was on the point of expiring, the spinners being unable to produce yarn to a profit, and their almost immediate effect was to reduce the cost of production, to improve immensely the quality of the manufacture, and to establish the British linen trade on a solid foundation. The production of flax machinery became an important branch of manufacture at Leeds, large quantities being made for home use as well as for exportation, giving employment to an increasing number of highly skilled mechanics. Mr. Murray's faculty for organising work, perfected by experience, enabled him also to introduce many valuable improvements in the mechanics of manufacturing. His preeminent skill in mill gearing became generally acknowledged, and the effects of his labours are felt to this day in the extensive and still thriving branches of industry which his ingenuity and ability mainly contributed to establish. All the machine tools used in his establishment were designed by himself, and he was most careful in the personal superintendence of all the details of their construction. Mr. Murray died at Leeds in 1826, in his 63rd year. We have not yet exhausted the list of claimants to the invention of the planing machine, for we find still another in the person of Richard Roberts of Manchester, one of the most prolific of modern inventors. Mr. Roberts has indeed achieved so many undisputed inventions that he can readily afford to divide the honour of this case with others. He has contrived things so various as the self-acting mule and the best electromagnet, wet gas meters and dry planing machines, iron billiard tables and turret clocks, the centrifugal railway and the drill slotting machine, an apparatus for making cigars, and machinery for the propulsion and equipment of steamships, so that he may almost be regarded as the admirable Crichton of modern mechanics. Richard Roberts was born in 1789 at Carrickhofa in the parish of Llanymynech. His father was by trade a shoemaker, to which he occasionally added the occupation of toll-keeper. The house in which Richard was born stood upon the border line which then divided the counties of Salop and Montgomery, the front door opening into the one county and the back door into the other. Richard, when a boy, received next to no education, and as soon as he was of fitting age was put to common labouring work. For some time he worked in a quarry near his father's dwelling, but being of an ingenious turn, he occupied his leisure hours in making various articles of mechanism, partly for amusement and partly for profit. One of his first achievements while working as a quarryman was a spinning wheel, of which he was very proud, for it was considered a good job. Thus he gradually acquired dexterity in handling tools, and he shortly came to entertain the ambition of becoming a mechanic. There were several ironworks in the neighbourhood, and thither he went in search of employment. He succeeded in finding work as a pattern maker at Bradley, near Bilston, under John Wilkinson, the famous ironmaster, a man of great enterprise as well as mechanical skill, for he was the first man, as already stated, that Watt could find capable of boring a cylinder with any approach to truth for the purpose of his steam engines. After acquiring some practical knowledge of the art of working in wood as well as iron, Roberts proceeded to Birmingham, where he passed through several different shops, gaining further experience in mechanical practice. He tried his hand at many kinds of work, and acquired considerable dexterity in each. He was regarded as a sort of jack of all trades, for he was a good turner, a tolerable wheelwright, and could repair millwork at a pinch. He next moved northward to the Horsley Ironworks, Tipton, where he was working as a pattern maker when he had the misfortune to be drawn in his own county for the militia. He immediately left his work and made his way homeward to Llanymynech, determined not to be a soldier or even a militiaman. But home was not the place for him to rest in, and after bidding a hasty adieu to his father, he crossed the county northward on foot to reach Liverpool, in the hopes of finding work there. Failing in that, he set out for Manchester and reached it at dusk, very weary and very miry in consequence of the road being in such a wretched state of mud and ruts. He relates that, not knowing a person in the town, he went up to an apple stall, ostensibly to buy a pennyworth of apples, but really to ask the stall-keeper if he knew of any person in want of a hand. Was there any turner in the neighbourhood? Yes, round the corner. Thither he went at once, found the wood turner in, and was promised a job on the following morning. He remained with the turner for only a short time, after which he found a job in Salford at lathe and tool making. But hearing that the militia warrant officers were still searching for him, he became uneasy and determined to take refuge in London. He trudged all the way on foot to that great hiding place, and first tried Holzapfels, the famous toolmakers, but failing in his application, he next went to Maudslay's and succeeded in getting employment. He worked there for some time, acquiring much valuable practical knowledge in the use of tools, cultivating his skill by contact with first-class workmen, and benefiting from the spirit of active contrivance which pervaded the Maudslay shops. His manual dexterity greatly increased, and his inventive ingenuity fully stimulated, he determined on making his way back to Manchester, which, even more than London itself, at that time presented abundant openings for men of mechanical skill. Hence we find so many of the best mechanics trained at Maudslay and Clement's, Nasmyth, Lewis, Muir, Roberts, Whitworth, and others, shortly rising into distinction there as leading mechanics and toolmakers. The mere enumeration of the various results of Mr. Roberts' inventive skill during the period of his settlement at Manchester as a mechanical engineer would occupy more space than we can well spare, but we may briefly mention a few of the more important. In 1816, while carrying on business on his own account at Deansgate, he invented his improved sector for correctly sizing wheels in blank previously to their being cut, which is still extensively used. In the same year he invented his improved screw lathe, and in the following year, at the request of the Borough Reeve and Constables of Manchester, he contrived an oscillating and rotating wet gas meter of a new kind, which enabled them to sell gas by measure. This was the first meter in which a water lute was applied to prevent the escape of gas by the index shaft, the want of which, as well as its great complexity, had prevented the only other gas meter then in existence from working satisfactorily. The water lute was immediately adopted by the patentee of that meter. The planing machine, though claimed as we have seen by many inventors, was constructed by Mr. Roberts after an original plan of his own in 1817, and became the tool most generally employed in mechanical workshops, acting by means of a chain and rack, though it has since been superseded to some extent by the planing machine of Whitworth, which works both ways upon an endless screw. Improvements followed in the slide lathe, giving a large range of speed with increased diameters for the same size of headstock, etc., in the wheel-cutting engine, in the scale beam, by which, with a load of 2 ounces on each end, the 1/1500th part of a grain could be indicated, in the broaching machine, the slotting machine, and other engines. But the inventions by which his fame became most extensively known arose out of circumstances connected with the cotton manufacture of Manchester and the neighbourhood. The great improvements which he introduced in the machine for making weavers' reeds led to the formation of the firm of Sharp, Roberts and Company, of which Mr. Roberts was the acting mechanical partner for many years. Not less important were his improvements in power looms for weaving fustians, which were extensively adopted. But by far the most famous of his inventions was unquestionably his self-acting mule, one of the most elaborate and beautiful pieces of machinery ever contrived. Before its invention, the working of the entire machinery of the cotton mill, as well as the employment of its piecers, cleaners, and other classes of operatives, depended upon the spinners, who, though receiving the highest rates of pay, were by much the most given to strikes, and they were frequently accustomed to turn out in times when trade was brisk, thereby bringing the whole operations of the manufactories to a standstill, and throwing all the other operatives out of employment. A long-continued strike of this sort took place in 1824, when the idea occurred to the masters that it might be possible to make the spinning mules run out and in at the proper speed by means of self-acting machinery, and thus render them in some measure independent of the more refractory class of their workmen. It seemed, however, to be so very difficult a problem that they were by no means sanguine of success in its solution. Some time passed before they could find any mechanic willing to so much as consider the subject. Mr. Ashton of Staley Bridge made every effort in this object, but the answer he got was uniformly the same. The thing was declared to be impracticable and impossible. Mr. Ashton, accompanied by 2 other leading spinners, called upon Sharp, Roberts and Company to seek an interview with Mr. Roberts. They introduced the subject to him, but he would scarcely listen to their explanations, cutting them short with the remark that he knew nothing whatever about cotton spinning. They insisted, nevertheless, on explaining to him what they required, but they went away without being able to obtain from him any promise of assistance in bringing out the required machine. The strike continued, and the manufacturers again called upon Mr. Roberts, but with no better result. A third time they called and applied to Mr. Sharp, the capitalist of the firm, who promised to use his best endeavours to induce his mechanical partner to take the matter in hand. But Mr. Roberts, notwithstanding his reticence, had been occupied in carefully pondering the subject since Mr. Ashton's first interview with him. The very difficulty of the problem to be solved had tempted him boldly to grapple with it, though he would not hold out the slightest expectation to the cotton spinners of his being able to help them in their emergency until he saw his way perfectly clear. That time had now come, and when Mr. Sharp introduced the subject, he said he had turned the matter over and thought he could construct the required self-acting machinery. It was arranged that he should proceed with it at once, and after a close study of 4 months he brought out the machine now so extensively known as the self-acting mule. The invention was patented in 1825 and was perfected by subsequent editions, which were also patented. Like so many other inventions, the idea of the self-acting mule was not new. Thus Mr. William Strutt of Derby, the father of Lord Belper, invented a machine of this sort at an early period. Mr. William Belly of the New Lanark Mills invented a second, and various other projectors tried their skill in the same direction, but none of these inventions came into practical use. In such cases it has become generally admitted that the real inventor is not the person who suggests the idea of the invention, but he who first works it out into a practicable process, and so makes it of practical and commercial value. This was accomplished by Mr. Roberts, who, working out the idea after his own independent methods, succeeded in making the first self-acting mule that would really act as such, and he is therefore fairly entitled to be regarded as its inventor. By means of this beautiful contrivance, spindle carriages, bearing hundreds of spindles, run themselves out and in by means of automatic machinery at the proper speed without a hand touching them, the only labour required being that of a few boys and girls to watch them and mend the broken threads when the carriage recedes from the roller beam, and to stop it when the cop is completely formed, as is indicated by the bell of the counter attached to the working gear. Mr. Baines describes the self-acting mule while at work as drawing out, twisting and winding up many thousand threads with unfailing precision and indefatigable patience and strength. A scene as magical to the eye which is not familiarized with it as the effects have been marvellous in augmenting the wealth and population of the country. Mr. Roberts' great success with the self-acting mule led to his being often appealed to for help in the mechanics of manufacturing. In 1826, the year after his patent was taken out, he was sent for to Mulhouse in Alsace to design and arrange the machine establishment of André Coquelin and Company, and in that and the 2 subsequent years he fairly set the works a-going, instructing the workmen in the manufacture of spinning machinery, and thus contributing largely to the success of the French cotton manufacture. In 1832 he patented his invention of the radial arm for winding on in the self-acting mule, now in general use, and in future years he took out sundry patents for roving, slubbing, spinning, and doubling cotton and other fibrous materials, and for weaving, beetling, and mangling fabrics of various sorts. A considerable branch of business carried out by the firm of Sharp, Roberts and Company was the manufacture of iron billiard tables, which were constructed with almost perfect truth by means of Mr. Roberts' planing machine, and became a large article of export. But a much more important and remunerative department was the manufacture of locomotives, which was begun by the firm shortly after the opening of the Liverpool and Manchester Railway had marked this as one of the chief branches of future mechanical engineering. Mr. Roberts adroitly seized the opportunity presented by this new field of invention and enterprise, and devoted himself for a time to the careful study of the locomotive and its powers. As early as the year 1829 we find him presenting to the Manchester Mechanics' Institute a machine exhibiting the nature of friction upon railroads, in solution of the problem then under discussion in the scientific journals. In the following year he patented an arrangement for communicating power to both driving wheels of the locomotive at all times in the exact proportions required when turning to the left or right, an arrangement which has since been adopted in many road locomotives and agricultural engines. In the same patent will be found embodied his invention of the steam brake, which was also a favourite idea of George Stephenson, since elaborated by Mr. McConnell of the London and North Western Railway. In 1834, Sharp, Roberts and Company began the manufacture of locomotives on a large scale, and the compactness of their engines, the excellence of their workmanship, and the numerous original improvements introduced in them, speedily secured for the engines of the Atlas firm a high reputation and a very large demand. Among Mr. Roberts' improvements may be mentioned his method of manufacturing the crank axle, of welding the rim and tyres of the wheels, and his arrangement and form of the wrought iron framing of the axle guards. His system of templates and gauges, by means of which every part of an engine or tender corresponded with that of every other engine or tender of the same class, was as great an improvement as Maudslay's system of uniformity of parts in other descriptions of machinery. In connection with the subject of railways, we may allude in passing to Mr. Roberts' invention of the Jacquard punching machine, a self-acting tool of great power, used for punching any required number of holes of any pitch into any pattern with mathematical accuracy in bridge or boiler plates. The origin of this invention was somewhat similar to that of the self-acting mule. The contractors for the Conway Tubular Bridge, while under construction in 1848, were greatly hampered by combinations among the workmen, and they despaired of being able to finish the girders within the time specified in the contract. The punching of the iron plates by hand was a tedious and expensive as well as inaccurate process, and the work was proceeding so slowly that the contractors found it absolutely necessary to adopt some new method of punching if they were to finish the work on time. In their emergency they appealed to Mr. Roberts, and endeavoured to persuade him to take the matter up. He at length consented to do so, and evolved the machine in question during his evening's leisure, for the most part while quietly sipping his tea. The machine was produced, the contractors were enabled to proceed with the punching of the plates independent of the refractory men, and the work was executed with a dispatch, accuracy, and excellence that would not otherwise have been possible. Only a few years since, Mr. Roberts added a useful companion to the Jacquard punching machine in his combined self-acting machine for shearing iron and punching both webs of angle or T-iron simultaneously to any required pitch. Though this machine, like others which have proceeded from his fertile brain, is ahead even of this fast manufacturing age, and has not yet come into general use, but is certain to do so before many years have elapsed. These inventions were surely enough for one man to have accomplished, but we have not yet done. The mere enumeration of his other inventions would occupy several pages. We shall merely allude to a few of them. One was his turret clock, for which he obtained the medal at the Great Exhibition of 1851. Another was his prize electromagnet of 1845. When this subject was first mentioned to him, he said he did not know anything of the theory or practice of electromagnetism, but he would try and find out. The result of his trying was that he won the prize for the most powerful electromagnet. One is placed in the museum at Peel Park, Manchester, and another with the Scottish Society of Arts, Edinburgh. In 1846 he perfected an American invention for making cigars by machinery, enabling a boy, working one of his cigar engines, to make as many as 5,000 in a day. In 1852 he patented improvements in the construction, propelling, and equipment of steamships, which have, we believe, been adopted to a certain extent by the Admiralty. And a few years later, in 1855, we find him presenting the Secretary of War with plans of elongated rifle projectiles to be used in smoothbore ordnance, with a view to utilize the old pattern gun. His head, like so many inventors of the time, being full of the mechanics of war, he went so far as to wait upon Louis Napoleon and lay before him a plan by which Sebastopol was to be blown down. In short, upon whatever subject he turned his mind, he left the impress of his inventive faculty. If it was imperfect, he improved it. If incapable of improvement and impracticable, he invented something entirely new, superseding it altogether. But with all his inventive genius, in the exercise of which Mr. Roberts has so largely added to the productive power of the country, we regret to say that he is not gifted with a commercial faculty. He has helped others in their difficulties, but forgotten himself. Many have profited by his inventions without even acknowledging the obligations which they owed to him. They have used his brains and copied his tools, and the sucked orange is all but forgotten. There may have been a want of worldly wisdom on his part, but it is lamentable to think that one of the most prolific and useful inventors of his time should, in his old age, be left to fight with poverty. Mr. Whitworth is another of the first-class toolmakers of Manchester, who has turned to excellent account his training in the workshops of Maudslay and Clement. He has carried fully out the system of uniformity in screw threads which they initiated, and he has still further improved the mechanism of the planing machine, enabling it to work both backwards and forwards by means of a screw and roller motion. His Jim Crow machine, so called from its peculiar motion in reversing itself and working both ways, is an extremely beautiful tool, adapted alike for horizontal, vertical, or angular motions. The minute accuracy of Mr. Whitworth's machines is not the least of their merits, and nothing will satisfy him short of perfect truth. At the meeting of the Institute of Mechanical Engineers at Glasgow in 1856, he read a paper on the essential importance of possessing a true plane as a standard of reference in mechanical constructions, and he described elaborately the true method of securing it, namely by scraping instead of by the ordinary process of grinding. At the same meeting he exhibited a machine of his own invention, by which he stated that a difference of a millionth part of an inch in length could at once be detected. He also there urged his favourite idea of uniformity and proper gradation of size of parts in all the various branches of the mechanical arts, as a chief means towards economy of production, a principle, as he showed, capable of very extensive application. To show the progress of tools and machinery in his own time, Mr. Whitworth cited the fact that 30 years since the cost of labour for making a surface of cast iron true, one of the most important operations in mechanics, by chipping and filing by the hand, was 12 shillings a square foot, whereas it is now done by the planing machine at a cost of labour of less than a penny. Then in machinery, pieces of 74-reed printing cotton cloth of 29 yards each could not be produced at less cost than 30 shillings 6pence per piece, whereas the same description is now sold for 3 shillings and 9pence. Mr. Whitworth has been among the most effective workers in this field of improvement, his tools taking the first place in point of speed, accuracy, and finish of work, in which respects they challenge competition with the world. Mr. Whitworth has of late years been applying himself with his accustomed ardour to the development of the powers of rifled guns and projectiles, a branch of mechanical science in which he confessedly holds a foremost place, and in perfecting which he is still occupied. End of chapter 14. Chapter 15, Part 1 of Industrial Biography, Ironworkers and Toolmakers by Samuel Smiles. This LibriVox recording is in the public domain. Recording by Clive Catterall. James Nasmyth. By hammer and hand all arts doth stand. Hammermen's motto. The founder of the Scotch family of Nasmyth is said to have derived his name from the following circumstance. In the course of the feuds which raged for some time between the Scotch kings and their powerful subjects, the Earls of Douglas, a rencontre took place one day on the outskirts of a border village, where the king's adherents were worsted. One of them took refuge in the village smithy, where, hastily disguising himself and donning a spare leathern apron, He pretended to be engaged in assisting the smith with his work, when a party of the Douglas followers rushed in. They glanced at the pretended workman at the anvil, and observed him deliver a blow upon it so unskilfully that the hammer shaft broke in his hand. On this, one of the Douglas men rushed at him, calling out, "You're nae smith!" The assailed man seized his sword, which lay conveniently at hand, and defended himself so vigorously that he shortly killed his assailant, while the smith brained another with his hammer. And a party of the king's men having come to their help, the rest was speedily overpowered. The royal forces then rallied, and their temporary defeat was converted into a victory. The king bestowed a grant of land on his follower Nasmyth, who assumed for his arms a sword between two hammers with broken shafts, and the motto "Non arte sed marte," as if to disclaim the art of the smith in which he had failed, and to emphasize the superiority of the warrior. Such is said to be the traditional origin of the family of Nasmyth of Possow in Peeblesshire, who continue to bear the same name and arms. It is remarkable that the inventor of the steam hammer should have so effectually contradicted the name he bears and reversed the motto of his family. For so far from being "nay Smith," he may not inappropriately be designated the very Vulcan of the 19th century. His hammer is a tool of immense power and pliancy, but for which we must have stopped short in many of those gigantic engineering works which are among the marvels of the age in which we live. It possesses so much precision and delicacy that it will chip the end of an egg resting in a glass on the anvil without breaking it, while it delivers a blow of 10 tons with such a force as to be felt shaking the parish. It is therefore with a high degree of appropriateness that Mr. Nasmyth has discarded the feckless hammer with the broken shafts, and assumed for his emblem his own magnificent steam hammer, at the same time reversing the family motto, which he has converted into "Non marte sed arte." James Nasmyth belongs to a family whose genius in art has long been recognised. His father, Alexander Nasmyth of Edinburgh, was a landscape painter of great eminence, whose works are sometimes confounded with those of his son Patrick, called the English Hobbema, though his own merits are peculiar and distinctive. The elder Nasmyth was also an admirable portrait painter, and his head of Burns, the best ever painted of the poet, bears ample witness. His daughters, the Misses Nasmyth, were highly skilled painters of landscape, and their works are well known and much prized. James, the youngest of the family, inherits the same love of art, though his name is more extensively known as a worker and inventor in iron. He was born at Edinburgh on the 19th of August, 1808, and his attention was early directed to mechanics by the circumstance of this being one of his father's hobbies. Besides being an excellent painter, Mr. Nasmyth had a good general knowledge of architecture and civil engineering, and could work at the lathe and handle tools with the dexterity of a mechanic. He employed nearly the whole of his spare time in a little workshop which adjoined his studio, where he encouraged his youngest son to work with him in all sorts of materials. Among his visitors at the studio were Professor Leslie, Patrick Miller of Dalswinton, and other men of distinction. He assisted Mr. Miller in his early experiments with paddle boats, which eventually led to the invention of the steamboat. It was a great advantage for the boy to be trained by a father who so loved excellence in all its forms, and could minister to his love of mechanics by his own instruction and practice. James used to drink in with pleasure and profit the conversation which passed between his father and his visitors on scientific and mechanical subjects, and as he became older, the resolve grew stronger in him every day that he would be a mechanical engineer and nothing else. At a proper age he was sent to the high school, then as now celebrated for the excellence of its instruction, and there he laid the foundation of a sound and liberal education. But he has himself told the simple story of his early life in such graphic terms that we feel we cannot do better than quote his own words. "I had the good luck," he says, "to have for a school companion the son of an iron founder. Every spare hour I could command was devoted to visits to his father's iron foundry, where I delighted to watch the various processes of moulding, iron melting, casting, forging, pattern making, and other smith and metal work. And although I was only about 12 years old at the time, I used to lend a hand in which hearty zeal did a good deal to make up for want of strength. I look back to the Saturday afternoons spent in the workshops of that small foundry as an important part of my education. I did not trust to reading about such and such things. I saw and handled them, and all the ideas in connection with them became permanent in my mind. I also obtained there, what was of much value to me in after life, a considerable acquaintance with the nature and character of workmen. By the time I was 15, I could work and turn out really respectable jobs in wood, brass, iron and steel. Indeed, in the working of the latter inestimable material, I had, at a very early age, 11 or 12, acquired considerable proficiency. As that was the pre-Lucifer match period, the possession of a steel and tinderbox was quite a patent of nobility among boys. So I used to forge old files into steels in my father's little workshop, and harden them, and produce such first-rate, neat little articles in that line that I became quite famous among my school companions, and many a task have I excused me by bribing the monitor, whose grim sense of duty never could withstand the glimpse of a steel. My first essay at making a steam engine was when I was 15. I then made a real working steam engine, 1 3/4 inches diameter cylinder and 8 inches stroke, which not only could act, but really did some useful work, for I made it grind the oil colours which my father required for his painting. Steam engine models, now so common, were exceedingly scarce in those days, and very difficult to be had. And as the demand for them arose, I found it both delightful and profitable to make them, as well as the sectional models of steam engines, which I introduced for the purpose of exhibiting the movements of all the parts, both exterior and interior. With the results of the sale of such models, I was enabled to pay the price of tickets of admission to the lecture on natural philosophy and chemistry, delivered in the University of Edinburgh. About the same time, 1826, I was so happy as to be employed by Professor Leslie in making models and portions of apparatus required by him for his lectures and philosophical investigations, and I also had the inestimable good fortune to secure his friendship. His admirably clear manner of communicating a knowledge of the fundamental principles of mechanical science rendered my intercourse with him of the utmost importance to myself. A hearty, cheerful, earnest desire to toil in his service caused him to take pleasure in instructing me by occasional explanations of what might otherwise have remained obscure. About the years 1827 and 1828, the subject of steam carriages for common roads occupied much of the attention of the public. Many tried to solve the problem. I made a working model of an engine which performed so well that some friends determined to give me the means of making one on a larger scale. This I did, and I shall never forget the pleasure and the downright hard work I had in producing, in the autumn of 1828, at an outlay of £60, a complete steam carriage that ran many a mile with 8 persons on it. After keeping it in action 2 months, to the satisfaction of all who were interested in it, my friends allowed me to dispose of it, and I sold it a great bargain, after which the engine was used in driving a small factory. I may mention that in the engine I employed the waste steam to cause an increased draught by its discharge up the chimney. This important use of the waste steam had been introduced by George Stephenson some years before, though entirely unknown to me. The earnest desire which I cherished of getting forward in the business of life induced me to turn my attention to obtaining employment in some of the great engineering establishments of the day, at the head of which, in my fancy, as well as in reality, stood that of Henry Maudslay of London. It was the summit of my ambition to get work in that establishment, but as my father had not the means of paying a premium, I determined to try what I could do towards attaining my object by submitting to Mr. Maudslay actual specimens of my capability as a young workman and draftsman. To this end I set to work and made a small steam engine, every part of which was the result of my own handiwork, including the casting and the forging of the several parts. This I turned out in such style as I should even now be proud of. My sample drawings were, I might say, highly respectable. Armed with such means of obtaining the good opinion of the great Henry Maudslay, on the 19th of May 1829, I sailed for London in a lathe smack, and after an 8 days' voyage saw the metropolis for the first time. I made bold to call on Mr. Maudslay and told him my simple tale. He desired me to bring my models for him to look at. I did so, and when he came to me, I could see by the expression of his cheerful, well-remembered countenance that I had attained my object. He then and there appointed me to be his own private workman, to assist him in his little paradise of a workshop, furnished with the models of improved machinery and engineering tools of which he had been the great originator. He left me to arrange as to the wages with his chief cashier, Mr. Robert Young, and on the first Saturday evening I accordingly went to the counting-house to inquire of him about my pay. He asked me what would satisfy me. Knowing the value of the situation I had obtained, and having a very modest notion of my worthiness to occupy it, I said that if he would not consider 10 shillings a week too much, I thought I could do very well with that. I suppose he concluded that I had some means of my own to live on besides the 10 shillings a week which I had asked. He little knew that I had determined not to cost my father another farthing when I left home to begin the world on my own account. My proposal was at once acceded to, and well do I remember the pride and delight I felt when I carried to my 3 shillings a week lodging that night my first wages. Ample they were in my idea, for I knew how little I could live on, and was persuaded that by strict economy I could easily contrive to make the money support me. To help me in this object, I contrived a small cooking apparatus, which I forthwith got made by a tinsmith in Lambeth at a cost of 6 shillings, and by its aid I managed to keep the eating and drinking part of my private account within 3 shillings and 6pence per week, or 4 shillings at the outside. I had 3 meat dinners a week, and generally 4 rice and milk dinners, all of which were cooked by my little apparatus, which I set in action after breakfast. The oil cost me not quite a halfpenny a day. The meat dinners consisted of a stew of from 1/2 to 3/4 pound of a leg of beef, the meat costing 3.5pence per pound, which, with sliced potatoes and a little onion, and as much water as just covered all, with a sprinkle of salt and black pepper, by the time I returned to dinner at 6:30, furnished a repast in every respect as good as my appetite. For breakfast I had coffee and a due proportion of quartern loaf. After the first year of my employment under Mr. Maudslay, my wages were raised to 15 shillings a week, and I then, but not till then, indulged in the luxury of butter to my bread. I am the more particular in all this to show you that I was a thrifty housekeeper, although only a lodger in a 3 shillings room. I have the old apparatus by me yet, and I shall have another dinner out of it ere I am a year older, out of regard to days that were full of the real romance of life. On the death of Henry Maudslay in 1831, I passed over to the service of his worthy partner, Mr. Joshua Field, and acted as his draftsman, much to my advantage, until the end of that year, when I returned to Edinburgh to construct a small stock of engineering tools for the purpose of enabling me to start in business on my own account. This occupied me until the spring of 1833, and during the interval I was accustomed to take in jobs to execute in my little workshop in Edinburgh, so as to obtain the means of completing my stock of tools. In June 1834 I went to Manchester, and took a flat of an old mill in Dale Street, where I began business. In 2 years my stock had so increased as to overload the floor of the old building to such an extent that the landlord, Mr. Wren, became alarmed, especially as the tenant below me, a glass cutter, had a visit from the end of a 20-horse engine beam one morning among his cut tumblers. To set their anxiety at rest, I went out that evening to Patricroft, and took a look at a rather choice bit of land, bounded on one side by the canal, and on the other by the Liverpool and Manchester Railway. By the end of the week I had secured a lease on the site for 999 years. By the end of the month my woodsheds were erected. The ring of the hammer on the smith's anvil was soon heard all over the place, and the Bridgewater foundry was fairly under way. There I toiled right heartily until December the 31st, 1856, when I retired to enjoy in active leisure the reward of a laborious life, during which, with the blessing of God, I enjoyed much true happiness through the hearty love which I always had for my profession. And I trust I may be allowed to say, without undue vanity, that I have left behind me some useful results of my labours in those inventions with which my name is identified, which have had no small share in the accomplishment of some of the greatest mechanical works of our age. If Mr. Nasmyth had accomplished nothing more than the invention of his steam hammer, it would have been enough to found a reputation. Professor Tomlinson described it as one of the most perfect of artificial machines and noblest triumphs of mind over matter that modern English engineers have yet developed. The hand hammer has always been an important tool, and in the form of the stone celt it was perhaps the first invented. When the hammer of iron superseded that of stone, it was found practicable in the hands of a cunning workman to execute by its means metalwork of great beauty and even delicacy. But since the invention of cast iron and the manufacture of wrought iron in large masses, the art of hammer working has almost become lost, and great artists, such as Matzes of Antwerp and Rukers of Nuremberg were, no longer think it worth their while to expend time and skill in working on so humble a material as wrought iron. It is evident from the marks of care and elaborate design which many of these early works exhibit that the workman's heart was in his work, and that his object was not merely to get it out of hand, but to execute it in first-rate artistic style. When the use of iron extended, and larger ironwork came to be forged for cannon, tools, and machinery, the ordinary hand hammer was found insufficient, and the helve or forge hammer was invented. This was usually driven by a water wheel or by oxen or horses. The tilt hammer was another form in which it was used, the smaller kinds being worked by the foot. Among Watt's various inventions was a tilt hammer of considerable power, which he first worked by means of a water wheel, and afterwards by a steam engine regulated by a flywheel. His first hammer of this kind was 120 pounds in weight. It was raised 8 inches before making each blow. Watt afterwards made a tilt hammer for Mr. Wilkinson of Bradley Forge of 7½ hundredweight, and it made 300 blows a minute. Other improvements were made in the hammer from time to time, but no material alteration was made in the power by which it was worked until Mr. Nasmyth took it in hand, and applying to it the force of steam, at once provided the worker in iron with the most formidable of machine tools. This important invention originated as follows. In the early part of 1837, the directors of the Great Western Steamship Company sent Mr. Francis Humphreys, their engineer, to consult Mr. Nasmyth as to some engineering tools of unusual size and power, which were required for the construction of the engines of the Great Britain steamship. They had determined to construct those engines on the vertical trunk engine principle, in accordance with Mr. Humphreys' designs, and very complete works were erected by them at their Bristol dockyard for the execution of the requisite machinery, the most important of the tools being supplied by Nasmyth and Gaskell. The engines were in hand when a difficulty arose with respect to the enormous paddle shaft of the vessel, which was of such a size of forging as had never before been executed. Mr. Humphreys applied to the largest engineering firms throughout the country for tenders on the price at which they would execute this part of work. But to his surprise and dismay, he found that not one of the firms he applied to would undertake so large a forging. In this dilemma he wrote to Mr. Nasmyth on the 24th of November, 1838, informing him of this unlooked-for difficulty. "I find," said he, "there is not a forge hammer in England or Scotland powerful enough to forge the paddle shaft of the engines for the Great Britain. What am I to do? Do you think I might dare use cast iron?" This letter immediately set Mr. Nasmyth a-thinking. How was it that existing hammers were incapable of forging a wrought iron shaft of 30 inches diameter? Simply because of their want of compass, or range and fall as well as power of blow. A few moments' rapid thought satisfied him that it was by rigidly adhering to the old traditional form of hand hammer, of which the tilt, though driven by steam, was only but a modification, that the difficulty had arisen. When even the largest hammer was tilted up to its full height, its range was so small that when a piece of work of considerable size was placed on the anvil, the hammer became gagged, and on such an occasion, when the forging required the most powerful blow, it received next to no blow at all, the clear space for fall being almost entirely occupied by the work on the anvil. The obvious remedy was to invent some method by which a block of iron should be lifted to a sufficient height above the object on which it was desired to strike a blow, and let the block fall down upon the work, guiding it in its descent by such simple means as should give the required precision in the percussive action of the falling mass. Following out this idea, Mr. Nasmyth at once sketched on paper his steam hammer, having it clearly before him in his mind's eye a few minutes after receiving Mr. Humphrey's letter narrating his unlooked-for difficulty. The hammer, as thus sketched, consisted of first an anvil on which to rest the work, second a block of iron constituting the hammer or blow-giving part, third an inverted steam cylinder to whose piston rod the block was attached. All that was then required to produce by such means a most effective hammer was simply to admit steam in the cylinder so as to act on the underside of the piston, and so raise the block attached to the piston rod, and by a simple contrivance to let the steam escape, and so permit the block rapidly to descend by its own gravity upon the work on the anvil. Such, in a few words, is the rationale of the steam hammer. By the same day's post, Mr. Nasmyth wrote to Mr. Humphreys, enclosing a sketch of the invention by which he proposed to forge the Great Britain paddle shaft. Mr. Humphreys showed it to Mr. Brunel, the engineer-in-chief of the company, to Mr. Guppy, the managing director, and to others interested in the undertaking, by all of whom it was heartily approved. Mr. Nasmyth gave permission to communicate his plans to such forge proprietors as might feel disposed to erect such a hammer to execute the proposed work, the only condition which he made being that, in the event of the hammer being adopted, he was to be allowed to supply it according to his own design. The paddle shaft of the Great Britain was, however, never forged. About that time the substitution of the screw for the paddle wheel as a means of propulsion of steam vessels was attracting much attention, and the performances of the Archimedes were so successful as to induce Mr. Brunel to recommend his directors to adopt the new power. They yielded to his entreaty. The great engines which Mr. Humphreys had designed were accordingly set aside, and he was required to produce fresh designs of engines suited for screw propulsion. The result was fatal to Mr. Humphreys. The labour, the anxiety, and perhaps the disappointment proved too much for him, and a brain fever carried him off, so that neither his great paddle shaft nor Mr. Nasmyth's steam hammer to forge it was any longer needed. End of Chapter 15, Part 1. Chapter 15, Part 2 of Industrial Biography, Ironworkers and Toolmakers by Samuel Smiles. This LibriVox recording is in the public domain. Recording by Clive Catterall. James Nasmyth, Part 2. The hammer was left to bide its time. No forge master would take it up. The inventor wrote to all the great firms, urging its superiority to every other tool for working malleable iron into all kinds of forge work. Thus he wrote and sent illustrative sketches of his hammer to Ackermans and Morgan of Bristol, to the late Benjamin Hick and Rushton and Eckersley of Bolton, to Howard and Ravenhill of Rotherhithe and other firms. But unhappily bad times for the iron trade had set in, and although all to whom he communicated his design were much struck by its simplicity and obvious advantages, the answer usually given was, "We have not orders enough to keep in work the forge hammers we already have, and we do not desire at present to add any new ones, however improved." At that time no patent had been taken out for the invention. Mr. Nasmyth had not yet saved money enough to enable him to do so on his own account, and his partner declined to spend money upon a tool that no engineer would give the firm an order for. No secret was made of the invention, and excepting to its owner, it did not seem to be worth one farthing. Such was the unpromising state of affairs when Monsieur Schneider of the Creusot Ironworks in France called at the Patricroft Works together with his practical mechanic, Monsieur Bourdon, for the purpose of ordering some tools of the firm. Mr. Nasmyth was absent on a journey at the time, but his partner, Mr. Gaskell, as an act of courtesy to the strangers, took the opportunity of showing them all that was new and interesting in regard to mechanism about the works. And among other things, Mr. Gaskell brought out his partner's sketch or scheme book, which lay in a drawer in the office, and showed them the design of the steam hammer, which no English firm would adopt. They were much struck with its simplicity and practical utility, and Monsieur Bourdon took careful note of its arrangements. Mr. Nasmyth, on his return, was informed of the visit of Messieurs Schneider and Bourdon, but the circumstance of their having inspected the design of his steam hammer seems to have been regarded by his partner as too trivial a matter to be repeated to him, and he knew nothing of the circumstance until his visit to France in April 1840. When passing through the works at Creusot with Monsieur Bourdon, Mr. Nasmyth saw a crankshaft of unusual size, not only forged in the piece, but punched. He immediately asked, "How did you forge that shaft?" Monsieur Bourdon's answer was, "Why, with your hammer, to be sure." Great indeed was Nasmyth's surprise, for he had never yet seen the hammer except in his own drawing. A little explanation soon cleared all up. Monsieur Bourdon said he had been so much struck with the ingenuity and simplicity of the arrangement, that he had no sooner returned than he had set to work, and had a hammer made in general accordance with the design Mr. Gaskell had shown him, and that its performance had answered his every expectation. He then took Mr. Nasmyth to see the steam hammer, and great was his delight at seeing the child of his brain in full and active work. It was not, according to Mr. Nasmyth's idea, quite perfect, and he readily suggested several improvements conformable with the original design, which Monsieur Bourdon forthwith adopted. On reaching England, Mr. Nasmyth at once wrote to his partner, telling him what he had seen, and urging that the taking out of a patent for the protection of the invention ought no longer to be deferred. But trade was still very much depressed, and, as the Patricroft firm needed all their capital to carry on their business, Mr. Gaskell objected to lock up any of it in engineering novelties. Seeing himself on the brink of losing his property in the invention, Mr. Nasmyth applied to his brother-in-law, William Bennet, Esquire, who advanced him the requisite money for the purpose, about £280, and the patent was secured in June 1840. The first hammer of 30 hundredweight was made for the Patricroft Works, with the consent of the partners, and in the course of a few weeks it was in full work. The precision and beauty of its action, the perfect ease with which it was managed, and the untiring force of its percussive blows, were the admiration of all who saw it. And from that moment the steam hammer became a recognized power in modern mechanics. The variety or gradation of its blows was such that it was found practicable to manipulate a hammer of 10 tons as easily as if it had only been of 10 ounces weight. It was under such complete control that while descending with its greatest momentum, it could be arrested at any point with even greater ease than any instrument used by hand. While capable of forging an Armstrong 100-pounder or the sheet anchor for a ship of the line, it could hammer a nail or crack a nut without bruising the kernel. When it came into general use, the facilities which it afforded for executing all kinds of forging had the effect of greatly increasing the quantity of work done, at the same time that expense was saved. The cost of making anchors was reduced by at least 50%, while the quality of the forging was improved. Before its invention, the manufacture of a shaft of 15 or 20 hundredweight required the concentrated exertions of a large establishment, and its successful execution was regarded as a great triumph of skill, whereas forgings of 20 or 30 tons weight are now things of almost everyday occurrence, Its advantages were so obvious that its adoption soon became general, and in the course of a few years Nasmyth steam hammers were to be found in every well-appointed workshop, both at home and abroad. Many modifications have been made in the tool by Condie, Morrison, Naylor, Rigby and others, but Nasmyth's was the father of them all, and still holds its ground. Among the important uses to which this hammer has of late been applied is the manufacture of iron plates for covering the ships of war, and the fabrication of the immense wrought iron ordnance of Armstrong, Whitworth and Blakely. But for the steam hammer, indeed, it is doubtful whether such weapons could have been made. It is also used for the remanufacture of iron in various other forms, to say nothing of the greatly extended use which it has been the direct means of effecting in wrought iron and steel forgings in every description of machinery, from the largest marine steam engines to the most nice and delicate parts of textile mechanism. It is not too much to say, observes a writer in the Engineer, that without Nasmyth's steam hammer we must have stopped short in many of those gigantic engineering works which, but for the decay of all wonder in us, will be the perpetual wonder of this age, and which have enabled our modern engineers to take rank above the gods of all mythologies. There is one use to which the steam hammer is now becoming extensively applied by some of our manufacturers that deserves especial mention, rather for the prospect which it opens to us than for what has already actually been accomplished. We allude to the manufacture of large articles in dies. At one manufactory in the country, railway wheels, for example, are being manufactured with enormous economy by this means. The various parts of the wheels are produced in quantity either by rolling or by dies under the hammer. These parts are brought together in their relative positions in a mould, heated to a welding heat, and then by a blow of the steam hammer furnished with dies, are stamped into a complete and all but finished wheel. It is evident that wherever wrought iron articles of a manageable size have to be produced in considerable quantities, the same process may be adopted, and the saving effected by the substitution of this for the ordinary forging process will doubtless, ere long, prove incalculable. For this, as for the many other advantageous uses of the steam hammer, we are primarily and mainly indebted to Mr. Nasmyth. It is right, therefore, that we should hold his name in honour. In fact, when we think of the universal service which this machine is rendering us, we feel that some special expression of our indebtedness to him would be a reasonable and grateful service. The benefit which he has conferred upon us is so great as to justly entitle him to stand side by side with the few men who have gained name and fame as great inventive engineers, and to whom we have testified our gratitude, usually, unhappily, when it was too late for them to enjoy it. Mr. Nasmyth subsequently applied the principle of the steam hammer in the pile driver, which he invented in 1845. Until its production, all piles had been driven by means of a small mass of iron falling upon the head of the pile with great velocity from a considerable height. The raising of the iron mass by means of the monkey being an operation that occupied much time and labour, with which the results were very incommensurate. Pile driving was, in Mr. Nasmyth's words, conducted on the artillery or cannonball principle, the action being excessive and the mass deficient, and adapted rather for destructive than impulsive action. In his new and beautiful machine, he applied the elastic force of steam in raising the ram or driving block, on which, the block being disengaged, its whole weight of 3 tons descended on the head of the pile, and the process being repeated 80 times in a minute, the pile was sent home with a rapidity that was quite marvellous compared with the old-fashioned system. In forming cofferdams for the piers and abutments of bridges, quays and harbours, and in piling the foundations of all kinds of masonry, the steam pile-driver was found of invaluable use by the engineer. At the first experiment made with the machine, Mr. Nasmyth drove a 14-inch pile 15 feet into hard ground, at a rate of 65 blows a minute. The driver was first used in forming the great steam dock at Davenport, where the results were very striking. It was shortly after employed by Robert Stephenson in piling the foundations of the great high-level bridge at Newcastle, and the border bridge at Berwick, as well as in several other of his great works. The saving of time effected by this machine was very remarkable, the rate being 1 to 1,800. That is, a pile could be driven in 4 minutes that before required 12 hours. One of the peculiar features of the invention was that of employing the pile itself as the support of the steam hammer part of the apparatus while it was being driven, so that the pile had the percussive action of the dead weight of the hammer as well as its lively blows to induce it to sink into the ground. The steam hammer sat, as it were, on the shoulders of the pile, while it dealt forth its ponderous blows on the pile head at the rate of 80 a minute, and as the pile sank, the hammer followed it down with never relaxing activity until it was driven home to the required depth. One of the most ingenious contrivances employed in the driver, which was also adopted in the hammer, was the use of steam as a buffer in the upper part of the cylinder, which had the effect of a recoil spring and greatly enhanced the force of the downward blow. In 1846, Mr. Nasmyth designed a form of steam engine after that of his steam hammer, which has been extensively adopted all over the world for screw ships of all size. The pyramidal form of the engine, and its great simplicity and get-at-ability of parts, together with the circumstance that all the weighty parts of the engine are kept low, have rendered it a universal favourite. Among the other labour-saving tools invented by Mr. Nasmyth may be mentioned the well-known planing machine for small work, called Nasmyth's steam arm, now used in every large workshop. It was contrived for the purpose of executing a large order for locomotives received from the Great Western Railway, and was found of great use in accelerating the work, especially in planing the links, levers, connecting rods, and smaller kinds of wrought iron work in those engines. His circular cutter for toothed wheels was another of his handy inventions, which shortly came into general use. In iron founding also he introduced a valuable practical improvement. The old mode of pouring the molten metal into the moulds was by means of a large ladle with 1 or 2 cross handles and levers, but many dreadful accidents occurred through a slip of the hand, and Mr. Nasmyth resolved, if possible, to prevent them. The plan he adopted was to fix a worm wheel on the side of the ladle, into which a worm was geared, and by this simple contrivance one man was enabled to move the largest ladle on its axis with perfect ease and safety. By this means the work was more promptly performed, and accidents entirely avoided. Mr. Nasmyth's skill in invention was backed by great energy and a large fund of common sense, qualities not often found united. These proved of much service to the concern of which he was the head, indeed constituted the vital force. The firm prospered as it deserved, and they executed orders not only for England, but for most countries in the civilized world. Mr. Nasmyth had the advantage of being trained in a good school, that of Henry Maudslay, where he had not only learnt handicraft under the eye of that great mechanic, but the art of organising labour, and, what is of great value to an employer, knowledge of the character of workmen. Yet the Nasmyth firm were not without their troubles as respected the mechanics in their employment, and on one occasion they had to pass through the ordeal of a very formidable strike. The manner in which the inventor of the steam hammer literally scotched this strike was very characteristic. A clever young man employed by the firm as a brass founder, being found to have a peculiar capacity for skilled mechanical work, had been advanced to the lathe. The other men objected to his being so employed on the ground that it was against the rules of the trade. "But he is a first-rate workman," replied the employers, "and we think it right to advance a man according to his conduct and his merits." "No matter," said the workman, "it is against the rules, and if you do not take the man from the lathe, we must turn out." "Very well. We hold to our right of selecting the best men for the best places, and we will not take the man from the lathe." The consequence was a general turnout. Pickets were set about the works, and any stray men who went thither to seek employment were waylaid, and if not induced to turn back, were maltreated or annoyed until they were glad to leave. The works were almost at a standstill. This state of things could not be allowed to go on, and the head of the firm bestirred himself accordingly with his usual energy. He went down to Scotland, searched all the best mechanical workshops there, and after a time succeeded in engaging 64 good hands. He forbade them coming by driblets, but held them together until there was a full freight, and then they came, with their wives, families, chests of drawers, and 8-day clocks, in a steamboat specially hired for their transport from Greenock to Liverpool. From thence they came by special train to Patricroft, where houses were in readiness for their reception. The arrival of so numerous, well-dressed and respectable a corps of workmen and their families was an event in the neighbourhood, and could not fail to strike the pickets with surprise. Next morning the 64 Scotchmen assembled in the yard at Patricroft, and after giving 3 cheers, went quietly to their work. The picketing went on for a little while longer, but it was of no use against a body of strong men who stood shoulder to shoulder, as the new hands did. It was even bruited about that there were more trains to follow. It very soon became clear that the back of the strike was broken. The men returned to their work, and the clever brass founder continued at his turning lathe, from which he speedily rose to still higher employment. Notwithstanding the losses and suffering occasioned by strikes, Mr. Nasmyth holds the opinion that they have, on the whole, produced much more good than evil. They have served to stimulate invention in an extraordinary degree. Some of the most important labour-saving processes now in common use are directly traceable to them. In the case of many of our most potent self-acting tools and machines, manufacturers could not be induced to adopt them until compelled to do so by strikes. This was the case with the self-acting mule, the wool-combing machine, the planing machine, the slotting machine, Nasmyth's steam arm, and many others. Thus, even in the mechanical world, they may be a soul of goodness in things evil. Mr. Nasmyth retired from business in December 1856. He had the moral courage to come out of the groove which he had so laboriously made for himself, and to leave a large and prosperous business, saying, "I have now enough of this world's goods. Let younger men have their chance." He settled down at his rural retreat in Kent, but not to lead a life of idle ease. Industry had become his habit, and active occupation was necessary to his happiness. He fell back upon the cultivation of those artistic tastes which are the heritage of his family. When a boy at the High School of Edinburgh, he was so skilful in making pen and ink illustrations on the margins of the classics, that he thus often purchased from his monitors exemptions from the lessons of the day. Nor had he ceased to cultivate the art during his residence at Patricroft, but was accustomed to fall back upon it for relaxation and enjoyment amid the pursuits of the trade. That he possesses remarkable fertility of imagination, and great skill in architectural and landscape drawing, as well as in the much more difficult art of delineating the human figure, will be obvious to anyone who has seen his works, more particularly his City of St. Anne's, the Fairies, and Everybody for Ever, which last was exhibited in Pall Mall, among the recent collections of works of art by amateurs and others for the relief of the Lancashire distress. He has also brought his common sense to bear on such unlikely subjects as the origin of the cuneiform character. The possession of a brick from Babylon set him thinking. How had it been manufactured? Its underside was clearly marked by the sedges of the Euphrates, upon which it had been laid to dry and bake in the sun. But how about those curious cuneiform characters? How had writing assumed so remarkable a form? His surmise was this, that the brickmakers, in telling their tale of bricks, used the triangular corner of another brick, and by pressing it down upon the soft clay, left behind it the triangular mark which the cuneiform character exhibits. Such marks repeated, and placed in different relations to each other, would readily represent any number. From the use of the corner of a brick in writing, the transition was easy to a pointed stick with a triangular end, by the use of which all the cuneiform characters can readily be produced upon the soft clay. This curious question formed the subject of an interesting paper read by Mr. Nasmyth before the British Association at Cheltenham. But the most engrossing of Mr. Nasmyth's later pursuits has been the science of astronomy, in which, by bringing a fresh, original mind to the observation of celestial phenomena, he has succeeded in making some of the most remarkable discoveries of our time. Astronomy was one of his favourite pursuits at Patricroft, and on his retirement became his serious study. By repeated observations with a powerful reflecting telescope of his own construction, he succeeded in making a very careful and minute painting of the craters, cracks, mountains and valleys of the moon's surface, for which a council medal was awarded him at the Great Exhibition of 1851. But the most striking discovery which he has made by means of a big telescope, the result of patient, continuous and energetic observation, has been that of the nature of the sun's surface, and the character of the extraordinary light-giving bodies, apparently possessed of voluntary action, moving across it, sometimes forming spots or hollows of more than 100,000 miles in diameter. The results of these observations were of so novel a character that astronomers for some time hesitated to receive them as facts. Yet so eminent an astronomer as Sir John Herschel does not hesitate now to describe them as a most wonderful discovery. According to Mr. Nasmyth's observations, says he, made with a very fine telescope of his own making, the bright surface of the sun consists of separate, insulated individual objects or things, all nearly or exactly of one certain definite size and shape, which is more like that of a willow leaf, as he describes them, than anything else. These leaves or scales are not arranged in any order, as those on a butterfly's wing are, but lie crossing one another in all directions, like what are called spills in the game of spillikins, except at the borders of a spot, where they point for the most part inwards towards the middle of the spot, presenting much the sort of appearance that the small leaves of some water plants or seaweeds do at the edge of a deep hole of clear water. The exceedingly definite shape of these objects, their exact similarity to one another, and the way in which they lie across and athwart each other, except where they form a sort of bridge across a spot, in which case they seem to affect a common direction, namely that of the bridge itself. All these characters seem quite repugnant to the notion of their being of vaporous or cloudy or a fluid nature. Nothing remains but to consider them as separate and independent sheets, flakes or scales, having some sort of solidity. And these flakes, be they what they may, and whatever may be said about the dashing of meteoric stones into the sun's atmosphere, etc., are evidently the immediate source of the solar light and heat, by whatever mechanism or whatever processes they may be enabled to develop and, as it were, elaborate these elements from the bosom of the non-luminous fluid in which they appear to float. Looked at in this point of view, we cannot refuse to regard them as organisms of some peculiar and amazing kind, and though it would be too daring to speak of such organisation as partaking of the nature of life, yet we do know that vital action is competent to develop heat and light, as well as electricity. These wonderful objects have been seen by others, as well as Mr. Nasmyth, so that there is no room for doubt of their reality. Such is the marvellous discovery made by the inventor of the steam hammer, as described by the most distinguished astronomer of the age. A writer in the Edinburgh Review, referring to the subject in a recent number, says it shows him to possess an intellect as profound as it is expert. Doubtless his training as a mechanic, his habits of close observation, and his ready inventiveness, which conferred so much power on him as an engineer, proved of equal advantage to him when labouring in the domain of physical science. Bringing a fresh mind of keen perception to his new studies, and uninfluenced by preconceived opinions, he saw them in new and original lights, and hence the extraordinary discovery above described by Sir John Herschel. Some 200 years since, a member of the Nasmyth family, Jean Nasmyth of Hamilton, was burnt for a witch, one of the last martyrs to ignorance and superstition in Scotland, because she read her Bible with 2 pairs of spectacles. Had Mr. Nasmyth lived then, he might, with his 2 telescopes of his own making, which bring the sun and moon into his chamber for him to examine and paint, have been taken for a sorcerer. But fortunately for him, and still more so for us, Mr. Nasmyth stands before the public of this age as not only one of its ablest mechanics, but as one of the most accomplished and original of scientific observers. End of chapter 15. Chapter 16, Part 1 of Industrial Biography, Ironworkers and Toolmakers by Samuel Smiles. This LibriVox recording is in the public domain. Recording by Clive Catterall. William Fairbairn. In science there is work for all hands, more or less skilled, and he is usually the most fit to occupy the highest posts who has risen from the ranks, and has experimentally acquainted himself with the nature of the work to be done in each and every, even the humblest, department. J. D. Forbes. The development of mechanical industry in England has been so rapid, especially as regards the wonders achieved by the machine tools above referred to, that it may almost be said to have been accomplished within the life of the present generation. When I first entered this city, said Mr. Fairbairn, in his inaugural address as President of the British Association at Manchester in 1861, the whole of the machinery was executed by hand. There were neither planing, slotting, nor shaping machines, and with the exception of very imperfect lathes and a few drills, the preparatory operations of construction were effected entirely by the hands of the workmen. Now everything is done by machine tools, with a degree of accuracy which the unaided hand could never accomplish. The automaton, or self-acting machine tool, has within itself an almost creative power. In fact, so great are its powers of adaptation that there is no operation of the human hand that it does not imitate. In a letter to the author, Mr. Fairbairn says, "The great pioneers of machine tool making were Maudslay, Murray of Leeds, Clement and Fox of Derby, who were ably followed by Nasmyth, Roberts and Whitworth of Manchester, and Sir Peter Fairbairn of Leeds." And Mr. Fairbairn might well have added by himself, for he has been one of the most influential and successful of mechanical engineers. William Fairbairn was born at Kelso on the 19th of February 1787. His parents occupied a humble but respectable position in life. His father, Andrew Fairbairn, was the son of a gardener in the employment of Mr. Bailey of Melliston, and lived at Smelholm, a village lying a few miles west of Kelso. Tracing the Fairbairns still further back, we find several of them occupying the station of portioners, or small lairds, at Earlston on the Tweed, where the family had been settled since the days of the Solemn League and Covenant. By his mother's side, the subject of our memoir is supposed to be descended from the ancient border family of Douglas. While Andrew Fairbairn, William's father, lived at Smelholm, Walter Scott was living with his grandmother in Smelholm, or Sandyknowe Tower, whither he had been sent from Edinburgh in the hope that the change of air would help the cure of his diseased hip joint. And Andrew, being 9 years his senior, and a strong youth for his age, was accustomed to carry the little patient about in his arms, until he was able to walk by himself. At a later period, when Miss Scott, Walter's aunt, removed from Smelholm to Kelso, the intercourse between the families was renewed. Scott was then an Edinburgh advocate, engaged in collecting materials for his Minstrelsy of the Scottish Border, or, as his aunt described his pursuit, running after the old wives in the country gathering havers. He used frequently to read over by the fireside, in the evening, the results of his curious industry, which, however, were not very greatly appreciated by his nearest relatives, and they did not scruple to declare that for the advocate to go about collecting balance was a mere waste of time as well as money. William Fairbairn's first schoolmaster was a decrepit old man who went by the name of Bowed Johnny Kerr, a Cameronian with a nasal twang, which his pupils learned much more readily than they did his lessons in reading and arithmetic, notwithstanding a liberal use of the tawse. Yet Johnny had a taste for music, and taught his pupils to sing their reading lessons, which was reckoned quite a novelty in education. After a short time, our scholar was transferred to the parish school of the town, kept by a Mr. White,
where he was placed under the charge of a rather severe helper, who, instead of the tawse, administered discipline by means of his knuckles, hard as horn, which he applied with a peculiar jerk to the crania of his pupils. At this school Willie Fairbairn lost the greater part of the singing accomplishment which he had acquired under Bowed Johnny, but he learned in lieu of them to read from Scott and Barrow's collections of prose and poetry, while he obtained some knowledge of arithmetic, in which he proceeded as far as the practice of the rule of 3. This constituted the whole stock of school learning up to his 10th year. Out of school hours he learned to climb the ruined walls of the old abbey of the town, and there was scarcely an arch or tower or cranny of it with which he did not become familiar. When in his 12th year, his father, who had been brought up to farm work and possessed considerable practical knowledge of agriculture, was offered the charge of a farm at Moy in Rossshire, belonging to Lord Seaforth of Bramah Castle. The farm was of about 300 acres, situated on the banks of the River Conan, some 5 miles from the town of Dingwall. The family travelled thither in a covered cart, a distance of 200 miles, through a very wild and hilly country, arriving at their destination at the end of October 1799. The farm, when reached, was found overgrown with whins and brushwood, and covered in many places with great stones and rocks. It was, in short, as nearly in a state of nature as it was possible to be. The house intended for the farmer's reception was not finished, and Andrew Fairbairn, with his wife and 5 children, had to take temporary refuge in a miserable hovel, very unlike the comfortable house which they had quitted at Kelso. By next spring, however, the new house was ready, and Andrew Fairbairn set vigorously to work at the reclamation of the land. After about 2 years' labours, it exhibited an altogether different appearance, and in place of whins and stones there were to be seen heavy crops of barley and turnips. The barren years of 1800 and 1801, however, pressed very hardly on Andrew Fairbairn, as on every other farmer of arable land. About that time Andrew's brother Peter, who acted as secretary to Lord Seaforth, and through whose influence the former had obtained the farm, left Bramah Castle for the West Indies with his lordship, who, notwithstanding his being both deaf and dumb, had been appointed to the governorship of Barbados. And in consequence of various difficulties which occurred shortly after his leaving, Andrew Fairbairn found it necessary to give up his holding, whereupon he engaged as steward to Mackenzie of Allengrange, with whom he remained for 2 years. While the family lived at Moy, none of the boys were put to school. They could not be spared from the farm and the household. Those of them that could not work afield were wanted to help nurse the younger children at home. But Andrew Fairbairn possessed a great treasure in his wife, who was a woman of much energy of character, setting before her children an example of patient industry, thrift, discreetness, and piety, which could not fail to exercise a powerful influence upon them in after life. And this of itself was an education which probably far more than compensated for the boys' loss of school culture during their life at Moy. Mrs. Fairbairn span and made all of the children's clothes, as well as the blankets and sheeting, and while in the Highlands she not only made her own and her daughters' dresses, and her sons' jackets and trousers, but her husband's coats and waistcoats, besides helping her neighbours to cut out their clothing for family wear. One of William's duties at home was to nurse his younger brother Peter, then a delicate child under 2 years old, and to relieve himself of the labour of carrying him about, he began the construction of a little waggon in which to wheel him. This was, however, a work of some difficulty, as all the tools he possessed were only a knife, a gimlet, and an old saw. With these implements, a piece of thin board and a few nails, he nevertheless contrived to make a tolerably serviceable waggon body. His chief difficulty consisted in making the wheels, which he contrived to surmount by cutting sections from the stem of a small alder tree, and with a red-hot poker he bored the requisite holes in their centres to receive the axle. The waggon was then mounted on its 4 wheels, and to the great joy of its maker was found to answer its purpose admirably. In it he wheeled his little brother, afterwards well known as Sir Peter Fairbairn, Mayor of Leeds, in various directions about the farm, and sometimes to a considerable distance from it. The vehicle was regarded on the whole as a decided success. His father encouraged him in his little feats of construction of a similar kind, and he proceeded to make and rig miniature boats and ships, and then miniature wind and water mills, in which last art he acquired such expertness that he had sometimes 5 or 6 mills going at a time. The machinery were all made with a knife, the waterspouts being formed by the bark of a tree, and the millstones represented by round discs of the same material. Such were the first constructive efforts of the future millwright and engineer. When the family removed to Allen Grange in 1801, the boys were sent to school at Munlachie, about 1.5 miles distant from the farm. The school was attended by about 40 barefoot boys in tartan kilts, and about 20 girls, all of the poorer class. The schoolmaster was one Donald Fraser, a good teach, but a severe disciplinarian. Under him, William made some progress in reading, writing, and arithmetic, and though he himself has often lamented the meagreness of his school instruction, it is clear from what he has since been enabled to accomplish that these early lessons were enough at all events to set him fairly on the road of self-culture, and proved the fruitful seed of much valuable intellectual labour, as well as of many excellent practical books. After 2 years' trial of his new situation, which was by no means satisfactory, Andrew Fairbairn determined again to remove southward with his family, and selling off everything, they set sail from Cromarty for Leith in June 1803. Having seen his wife and children temporarily settled at Kelso, he looked out for a situation, and shortly after proceeded to undertake the management of Sir William Ingleby's farm at Ripley in Yorkshire. Meanwhile, William was placed for 3 months under the charge of his uncle William, the parish schoolmaster of Galashiels, for the purpose of receiving instruction in bookkeeping and land surveying, from which he derived considerable benefit. He could not, however, remain longer at school, for being of the age of 14, it was thought necessary that he should be set to work without further delay. His first employment was on the fine new bridge at Kelso, then in course of construction after the designs of Mr. Rennie. But in helping one day to carry a hand-barrow load of stone, his strength proving insufficient, he gave way under it, and the stones fell upon him, one of them inflicting a serious wound on his leg, which kept him a cripple for months. In the meantime, his father, being dissatisfied with his prospects at Ripley, accepted the appointment of manager of the Percy Main Colliery Company's farm in the neighbourhood of Newcastle on Tyne, whither he proceeded with his family towards the end of 1803, William joining them in the following February, when the wound in his leg was sufficiently healed to enable him to travel. Percy Main is situated within 2 miles of North Shields, and is one of the largest collieries in that district. William was immediately set to work at the colliery, his first employment being to lead coals from behind the screens to the pitmen's houses. His Scotch accent, and perhaps his awkwardness, exposed him to much annoyance from the pit lads, who were a very rough and profligate set, and as boxing was a favourite pastime among them, our youth had to fight his way to their respect, passing through a campaign of no less than 17 pitched battles. He was several times on the point of abandoning the work altogether, rather than undergo the buffetings and insults to which he was almost a daily martyr, when a protracted contest with one of the noted boxers of the colliery, in which he proved the victor, at length relieved him from further persecution. In the following year, at the age of 16, he was articled as an engineer for 5 years to the owners of Percy Main, and was placed under the charge of Mr. Robinson, the engine-wright of the colliery. His wages as apprentice were 8 shillings a week, but by working over hours, making wooden wedges used in pit work, and blocking out segments of solid oak required for walling the sides of the mine, he considerably increased his earnings, which enabled him to add to the gross income of the family, who was still struggling with the difficulties of small means and increasing expenses. When not engaged upon overwork in the evenings, he occupied himself in self-education. He drew up a scheme of daily study with this object, to which he endeavoured to adhere as closely as possible, devoting the evenings of Mondays to mensuration and arithmetic, Tuesdays to history and poetry, Wednesdays to recreation, novels and romances, Thursdays to algebra and mathematics, Fridays to Euclid and trigonometry, Saturdays to recreation, and Sundays to church, Milton, and recreation. He was enabled to extend the range of his reading by the help of the North Shields subscription library, to which his father entered him as a subscriber. Portions of his spare time were also occasionally devoted to mechanical construction, in which he cultivated the useful art of handling tools. One of his first attempts was the contrivance of a piece of machinery worked by a weight and pendulum that should at the same time serve for timepiece and orrery. But his want of means, as well as of time, prevented him from prosecuting this contrivance to completion. He was more successful with the construction of a fiddle, on which he was ambitious to become a performer. It must have been a tolerable instrument, for a professional player offered him 20 shillings for it. But though he succeeded in making a fiddle, and for some time persevered in the attempt to play upon it, he did not succeed in producing any satisfactory melody, and at length gave up the attempt, convinced that nature had not intended him for a musician. In due course of time, our young engineer was removed from the workshop, and appointed to take charge of the pumps of the mine and the steam engine by which they were kept in work. This employment was more to his taste, gave him better insight, and afforded him greater opportunities for improvement. The work was, however, very trying, and at times severe, especially in winter, the engineer being liable to be drenched with water every time he descended the shaft to regulate the working of the pumps. But thanks to a stout constitution, he bore these exposures without injury, though others sank under them. At this period he had the advantage of occasional days of leisure, to which he was entitled by reason of his night work, and during such leisure hours he usually applied himself to reading and study. It was about this time that William Fairbairn made the acquaintance of George Stephenson, while the latter was employed in working the ballast engine at Willington Quay. He greatly admired George as a workman, and was accustomed in the summer evenings to go over to the quay occasionally and take charge of George's engine to enable him to earn a few shillings extra by heaving ballast out of the collier vessels. Stephenson's zeal in the pursuit of mechanical knowledge probably was not without its influence in stimulating William Fairbairn himself to carry on so diligently the work of self-culture. But little could the latter have dreamt, while serving his apprenticeship at Percy Main, that his friend George Stephenson, the brakesman, should yet be recognised as among the greatest engineers of his age, and that he himself should have the opportunity, in his capacity of President of the Institute of Mechanical Engineers at Newcastle, of making public acknowledgment of the opportunities for education which he had enjoyed in that neighbourhood in his early years. Having finished his 5 years' apprenticeship at Percy Main, by which time he had reached his 21st year, William Fairbairn shortly after determined to go forth into the world in search of experience. At Newcastle he found employment as a millwright for a few weeks, during which he worked at the erection of a sawmill in the Close. From thence he went to Bedlington at an advanced wage. He remained there for 6 months, during which he was so fortunate as to make the acquaintance of Miss Marr, who, 5 years after, when his wanderings had ceased, became his wife. On the completion of the job on which he had been employed, our engineer prepared to make another change. Work was difficult to be had in the north, and joined by a comrade he resolved to try his fortune in London. Adopting the cheapest route, he took passage by a Shields collier, in which he sailed for the Thames on the 11th of December, 1811. It was then wartime, and the vessel was very short-handed, the crew consisting of only 3 old men and 3 boys, with the skipper and mate, so that the vessel was no sooner fairly at sea than both the passenger youths had to lend a hand in working her, and this continued for the greater part of the voyage. The weather was very rough, and in consequence of the captain's anxiety to avoid privateers, he hugged the shore too close, and when navigating the inside passage of the Swin between Yarmouth and the Nore, the vessel very narrowly escaped shipwreck. After beating along shore,
the captain half drunk the greater part of the time, the vessel at last reached the Thames, with loss of spars and an anchor, after a tedious voyage of 14 days. On arriving off Blackwall, the captain went ashore ostensibly in search of the coal exchange, taking our young engineer with him. The former was still under the influence of drink, and though he failed to reach the exchange that night, he succeeded in reaching a public house in Wapping, beyond which he could not be got. At 10 o'clock the two started on their return to the ship, but the captain took the opportunity of the darkness to separate from his companion, and did not reach the ship until next morning. It afterwards came out that he had been taken up and lodged at the watch-house. The youth, left alone in the streets of the strange city, felt himself in an awkward dilemma. He asked the next watchman he met to recommend him to a lodging, on which the man took him to a house in New Gravel Lane, where he succeeded in finding accommodation. What was his horror next morning to learn that a whole family, the Williamsons, had been murdered in the very next house during the night. Making the best of his way back to the ship, he found that his comrade, who had suffered dreadfully from seasickness during the voyage, had nearly recovered and was able to accompany him to the city in search of work. They had between them a sum of only about £8, so that it was necessary for them to take immediate steps to obtain employment. They thought themselves very fortunate in getting the promise of a job from Mr. Rennie, the celebrated engineer, whose works were situated at the south end of Blackfriars Bridge. Mr. Rennie sent the two young men to his foreman with a request that he should set them to work. The foreman referred them to the secretary of the Millwrights' Society, the shop being filled with union men, who set their shoulders together to exclude those of their own grade, however skilled, who could not produce evidence that they had complied with the rules of the trade. Describing his first experience of London Unionists, nearly half a century later, before an assembly of working men at Derby, Mr. Fairbairn said, "When I first entered London, a young man from the country had no chance whatever of success, in consequence of the trade guilds and unions. I had no difficulty in finding employment, but before I could begin work I had to run the gauntlet of the trade societies. And after dancing attendance for nearly 6 weeks, with very little money in my pocket, and having to box Harry all the time, I was ultimately declared illegitimate, and sent adrift to seek my fortune elsewhere. There were then 3 millwright societies in London, one called the Old Society, another the New Society, and a third the Independent Society. These societies were not founded for the protection of the trade, but for the maintenance of high wages, and for the exclusion of all those who could not assert their claims to work in London and other corporate towns. Laws of a most arbitrary character were enforced, and they were governed by cliques of self-appointed officers who never failed to take care of their own interests. Their first application for leave to work in London having thus disastrously ended, the two youths determined to try their fortune in the country, and with aching hearts they started next morning before daylight. Their hopes had been suddenly crushed, their slender funds were nearly exhausted, and they scarce knew where to turn. But they set their faces bravely northward, and pushed along the high road through slush and snow as far as Hertford, which they reached after nearly 8 hours' walking, on the moderate fare during their journey of a penny roll and a pint of ale each. Though wet to the skin, they immediately sought out a master millwright, and applied for work. He said he had no job vacant at present, but seeing their sorry plight, he had compassion upon them, and said, "Though I cannot give you employment, you seem to be 2 nice lads," and he concluded by offering Fairbairn a half-crown. But his proud spirit revolted at taking money which he had not earned, and he declined the proffered gift with thanks, saying he was sorry they could not have work. He then turned away from the door, on which his companion, mortified by his refusal to accept the half-crown at a time when they were reduced almost to their last penny, broke out in bitter remonstrances and regrets. Weary, wet, and disheartened, the two turned into Hertford churchyard, and rested for a while upon a tombstone, Fairbairn's companion relieving himself with a good cry and occasional angry outbursts of, "Why didn't you take the half-crown?"
"Come, come, man," said Fairbairn. "It's of no use crying. Cheer up. Let's try another road. Something must soon cast up." They rose and set out again. When they reached the bridge, the dispirited youth again broke down, and leaning his back against the parapet, said, "I winna gang a bit further. Let's get back to London." Against this Fairbairn remonstrated, saying, "It's of no use lamenting. We must try what we can do here. If the worst comes to the worst, we can list. You're a strong chap. They'll soon take you. And as for me, I'll join too. I think I could fight a bit." After this council of war, the pair determined to find lodgings in the town for the night, and begin their search for work anew on the morrow. Next day, when passing along one of the back streets of Hertford, they came to a wheelwright's shop, where they made the usual inquiries. The wheelwright said that he did not think there was any job to be had in the town, but if the two young men pushed on to Cheshunt, he thought they might find work at the windmill, which was under contract to be finished in 3 weeks, and where the millwright wanted hands. Here was a glimpse of hope at last, and the strength and spirits of both revived in an instant. They set out immediately, walked the 7 miles to Cheshunt, succeeded in obtaining the expected employment, worked at the job a fortnight, and entered London again with nearly £3 in their pockets. Our young millwright at length succeeded in obtaining regular employment in the metropolis at good wages. He worked first at Grundy's patent ropery at Shadwell, and afterwards at Mr. Penn's of Greenwich, gaining much valuable insight and sedulously improving his mind by study in his leisure hours. Among the acquaintances he then made was an enthusiastic projector of the name of Hall, who had taken out one patent for making hemp from beanstalks, and contemplated taking out another for effecting spade tillage by steam. The young engineer was invited to make the requisite model, which he did, and it cost him both time and money, which the out-at-elbows projector was unable to repay, and all that came of the project was the exhibition of the model at the Society of Arts and before the Board of Agriculture, in whose collection it is probably still to be found. Another more successful machine constructed by Mr. Fairbairn about the same time was a sausage-chopping machine, which he contrived and made for a pork butcher for £33. It was the first order he had ever had on his own account, and as the machine, when made, did its work admirably, he was naturally very proud of it. The machine was provided with a flywheel and double crank, with connecting rods which worked a crosshead. It contained a dozen knives crossing each other at right angles in such a way as to enable them to mince or divide the meat on a revolving block. Another part of the apparatus accomplished the filling of the sausages in a very expert manner, to the entire satisfaction of the pork butcher. As work was scarce in London at the time, and our engineer was bent on gathering further experience in his trade, he determined to make a tour of the south of England and South Wales, and set out from London in April 1813 with £7 in his pocket. After visiting Bath and Frome, he settled to work for 6 weeks at Bathgate, after which he travelled by Bradford and Trowbridge, always on foot, to Bristol. From thence he travelled through South Wales, spending a few days each at Newport, Llandaff, and Cardiff, where he took ship for Dublin. By the time he reached Ireland, his means were all but exhausted, only 3 halfpence remaining in his pocket. But being young, hopeful, skilful, and industrious, he was light of heart and looked cheerfully forward. The next day he succeeded in finding employment at Mr. Robinson's of the Phoenix Foundry, where he was put to work at once upon a set of patents for some nail machinery. Mr. Robinson was a man of spirit and enterprise, and seeing the quantities of English machine-made nails imported into Ireland, he was desirous of giving Irish industry the benefit of the manufacture. The construction of the nail-making machinery occupied Mr. Fairbairn the entire summer, and on its completion he set sail in the month of October for Liverpool. It may be added that, notwithstanding the expense incurred by Mr. Robinson in setting up the new nail machinery, his workmen threatened him with a strike if he ventured to use it. As he could not brave the opposition of the Unionists, then all-powerful in Dublin, the machinery was never set to work. The nail-making trade left Ireland never to return, and the Irish market was thenceforward supplied entirely with English-made nails. The Dublin iron manufacture was ruined in the same way, not through any local disadvantages, but solely by the prohibitory regulations enforced by the workmen of the trades unions. Arrived at Liverpool after a voyage of 2 days, which was then considered a fair passage, our engineer proceeded to Manchester, which had already become the principal centre of manufacturing operations in the north of England. As we have already seen in the memoirs of Nasmyth, Roberts, and Whitworth, Manchester offered great attractions for highly skilled mechanics, and it was as fortunate for Manchester as for William Fairbairn himself that he settled down there as a working millwright in the year of 1814, bringing with him no capital, but an abundance of energy, skill, and practical experience in his trade. Afterwards describing the characteristics of the millwright of that time, Mr. Fairbairn said, "In those days a good millwright was a man of large resources. He was generally well educated, and could draw out his own designs and work at the lathe. He had a knowledge of mill machinery, pumps, and cranes, and can turn his hand to the bench or the forge with equal adroitness and facility. If hard pressed, as was frequently the case in country places far from towns, he could devise for himself expedients which enabled him to meet the special requirements and complete his work without assistance. This was the class of men with whom I associated in early life, proud of their calling, fertile in resources, and aware of their value in a country where the industrial arts were rapidly developing." End of Chapter 16, Part 1. Chapter 16, Part 2 of Industrial Biography, Ironworkers and Toolmakers by Samuel Smiles. This LibriVox recording is in the public domain. Recording by Clive Catterall. William Fairbairn. When William Fairbairn entered Manchester, he was 24 years of age, and his hat still covered his family. But being now pretty well satiated with his Wanderschaft, as German tradesmen term their stage of travelling in search of trade experience, he desired to settle, and if fortune favoured him, to marry the object of his affections, to whom his heart still faithfully turned during all his wanderings. He succeeded in finding employment with Mr. Adam Parkinson, remaining with him for 2 years, working as a millwright at good wages. Out of his earnings he saved sufficient to furnish a 2-roomed cottage comfortably, and there we find him fairly installed with his wife by the end of 1816. As in the case of most men of a thoughtful turn, marriage served not only to settle our engineer, but to stimulate him to more energetic action. He now began to aim at taking a higher position, and entertained the ambition of beginning business on his own account. One of his first efforts in this direction was the preparation of the design of a cast-iron bridge over the Irwell at Blackfriars, for which a prize was offered. The attempt was unsuccessful, and a stone bridge was eventually decided on, but the effort made was creditable, and proved the beginning of many designs. The first job he executed on his own account was the erection of an iron conservatory and hothouse for Mr. J. Hulme of Clayton, near Manchester, and he induced one of his shopmates, James Lilly, to join him in the undertaking. This proved the beginning of a business connection which lasted for a period of 15 years, and laid the foundation of a partnership, the reputation of which, in connection with mill work and the construction of iron machinery generally, eventually became known all over the civilized world. Although the patterns for the conservatory were all made and the castings were begun, the work was not proceeded with, in consequence of the notice given by a Birmingham firm that the plan after which it was proposed to construct it was an infringement of their patent. The young firm were consequently under the necessity of looking about them for other employment, and to be prepared for executing orders, they proceeded in the year of 1817 to hire a small shed at a rate of 12 shillings a week, in which they set up a lathe of their own making, capable of turning shafts from 3 to 6 inches diameter, and they hired a strong Irishman to drive the wheel and assist at the heavy work. Their first job was the erection of a cullender, at the next a calico polishing machine. But orders came in slowly, and James Lilly began to despair of success. His more hopeful partner strenuously urged him to perseverance, and so buoyed him up with hopes of orders that he determined to go on a little longer. They then issued cards among the manufacturers, and made a tour of the principal firms, offering their services in soliciting work. Amongst others, Mr. Fairbairn called upon the Messrs. Adam and George Murray, the large cotton spinners, taking with him the designs of his iron bridge. Mr. Adam Murray received him kindly, heard his explanations, and invited him to call on the following day with his partner. The manufacturer must have been favourably impressed by his interview, for next day, when Fairbairn and Lilly called, he took them over his mill, and asked whether they felt themselves competent to renew with horizontal cross shafts the whole of the work by which the mule spinning machinery was turned. This was a formidable enterprise for a young firm without capital, and almost without plant, to undertake. But they had confidence in themselves, and boldly replied that they were willing and able to execute the work. On this, Mr. Murray said he would call and see them at their own workshop, to satisfy himself that they possessed the means of undertaking such an order. This proposal was by no means encouraging to the partners, who feared that when Mr. Murray spied the nakedness of the land in that quarter, he might repent him of his generous intentions. He paid his promised visit, and it is probable that he was more favourably impressed by the individual merits of the partners than by the excellence of their machine tools, of which they had only one, the lathe which they had just made and set up. Nevertheless, he gave them the order, and they began with glad hearts and willing hands and minds to execute this, their first contract. It may be sufficient to state that by working late and early, from 5 in the morning until 9 at night, for a considerable period, they succeeded in completing the alterations within the time specified and to Mr. Murray's entire satisfaction. The practical skill of the young men being thus proved, and their anxiety to execute the work entrusted to them to the best of their ability having excited the admiration of their employer, he took the opportunity of recommending them to his friends in the trade, and amongst others to Mr. John Kennedy of the firm of McConnell and Kennedy, then the largest spinners in the kingdom. The cotton trade had by this time sprung into great importance, and was increasing with extraordinary rapidity. Population and wealth were pouring into South Lancashire, and industry and enterprise were everywhere on foot. The foundations were being laid of a system of manufacturing in iron, machinery, and textile fabrics of nearly all kinds, the like of which has perhaps never been surpassed in any country. It was a race of industry, in which the prizes were won by the swift, the strong, and the skilled. For the most part, the early Lancashire manufacturers started very nearly equal in point of worldly circumstances, men originally of the smallest means often coming to the front, workmen, weavers, mechanics, pedlars, farmers, or labourers, in course of time rearing immense manufacturing concerns by sheer force of industry, energy, and personal ability. The description given by one of the largest employers in Lancashire of the capital with which he started might apply to many of them. "When I married," said he, "my wife had a spinning wheel and I had a loom. That was the beginning of our fortune." As an illustration of the rapid rise of Manchester men from small beginnings, the following outline of John Kennedy's career, intimately connected as he was with the subject of our memoir, may not be without interest in this place. John Kennedy was one of 5 young men of nearly the same age, who came from the same neighbourhood in Scotland, and eventually settled in Manchester as cotton spinners about the end of last century. The others were his brother James, his partner James McConnell, and the brothers Murray above referred to, Mr. Fairbairn's first extensive employers. John Kennedy's parents were respectable peasants, possessed of a little bit of ground at Knocknalling, in the stewartry of Kirkcudbright, on which they contrived to live, and that was all. John was one of a family of 5 sons and 2 daughters, and the father dying early, the responsibility and toil of bringing up these children devolved upon the mother. She was a strict disciplinarian, and early impressed upon the minds of her boys that they had their own way to make in the world. one of the first things she made them think about was the learning of some useful trade for the purpose of securing an independent living. "For," said she, "if you have gotten mechanical skill and intelligence, and are honest and trustworthy, you will always find employment, and be ready to avail yourselves of opportunities for advancing yourselves in life." Though the mother desired to give her sons the benefits of school education, there was but little of that commodity to be had in the remote district of Knocknalling. The parish school was 6 miles distant, and the teaching given in it was of a very inferior sort, usually administered by students, probationers for the ministry, or by half-fledged dominies, themselves more needing instruction than able to impart it. The Kennedys could only attend the school during a few months in summer-time, so that what they had acquired by the end of one season was often forgotten by the beginning of the next. They learned, however, to read the Testament, say their catechism, and write their own names. As the children grew up, they each longed for the time to come when they could be put to a trade. The family were poorly clad, stockings and shoes were luxuries rarely indulged in, and Mr. Kennedy used in after life to tell his grandchildren of a certain Sunday which he remembered shortly after his father died, when he was setting out for Dalry Church, and had borrowed his brother Alexander's stockings. His brother ran after him and cried, "See that you keep out of the dirt, for mind you've got my stockings on." John indulged in many daydreams about the world that lay beyond the valley and the mountains which surrounded the place of his birth. Though a mere boy, the natural objects, eternally unchangeable, which daily met his eyes, the profound silence of the scene, broken only by the bleating of a solitary sheep, or the crowing of a distant cock, or the thrasher beating out with his flail the scanty grain of the black oats spread upon a skin in the open air, or the streamlets leaping from the rocky clefts, or the distant church bell sounding up the valley on Sundays, all bred in his mind a profound melancholy and feeling of loneliness, and he used to think to himself, "What can I do to see and know something of the world beyond this?" The greatest pleasure he experienced during that period was when packmen came round with their stores of clothing and hardware, and displayed them for sale. He eagerly listened to all that such visitors had to tell of the ongoings of the world beyond the valley. The people of the Knocknalling district were very poor. The greater part of them were unable to support the younger members, whose custom it was to move off elsewhere in search of a living when they arrived at working years, some to America, some to the West Indies, and some to the manufacturing districts of the south. Whole families took their departure in this way, and the few friendships which Kennedy formed among those of his own age were thus suddenly snapped, and only a great blank remained. But he too could follow their example and enter upon that wider world in which so many others had ventured and succeeded. As early as 8 years of age, his mother still impressing upon her boys the necessity of learning to work, John gathered courage to say to her that he wished to leave home and apprentice himself to some handicraft business. Having seen some carpenters working in the neighbourhood, with good clothes on their backs, and hearing the men's characters well spoken of, he thought it would be a fine thing to be a carpenter too, particularly as the occupation would enable him to move from place to place and see the world. He was, as yet, however, of too tender an age to set out on the journey of life. But when he was about 11 years old, Adam Murray, one of his most intimate acquaintances, having gone off to serve an apprenticeship in Lancashire with Mr. Cannon of Chowbent, himself a native of that district, the event again awakened in him a strong desire to migrate from Knocknalling. Others had gone after Murray, James McConnell, and 2 or 3 more, and at length, at about 14 years of age, Kennedy himself left his native home for Lancashire. About the time that he set out, Paul Jones was ravaging the coasts of Galloway and producing general consternation throughout the district. Great excitement also prevailed through the occurrences of the Gordon riots in London, which extended into remote country places. And Kennedy remembered being nearly frightened out of his wits on one occasion by a poor dominie whose school he attended, who preached to his boys about the horrors that were coming upon the land through the introduction of popery. The boy set out for England on the 2nd of February, 1784, mounted upon a Galloway, his little package of clothes and necessaries strapped behind him. As he passed along the glen, recognizing each familiar spot, his heart was in his mouth, and he dared scarcely trust himself to look back.
The ground was covered with snow, and nature quite frozen up. He had the company of his brother Alexander as far as the town of New Galloway, where he slept the first night. The next day, accompanied by one of his future masters, Mr. James Smith, a partner of Mr. Cannon's, who had originally entered his service as a workman, they started on ponyback for Dumfries. After a long day's ride, they entered the town in the evening, and among the things which excited the boys' surprise were the few street lamps of the town, and a waggon with 4 horses and 4 wheels. In his remote valley, carts were as yet unknown, and even in Dumfries itself they were comparative rarities, the common means of transport in the district being what were called tumbling cars. The day after, they reached Longtown and slept there, the boy noting another lamp. The next stage was to Carlisle, where Mr. Smith, whose firm had supplied a carding engine and a spinning jenny to a small manufacturer in the town, went to gate and trim them. One was put up in a small house, the other in a small room, and the sight of these machines was John Kennedy's first introduction to cotton spinning. While going up the inn stairs, he was amazed, and not a little alarmed, at seeing 2 men in armour. He had heard of the battles between the Scots and the English, and believed these to be some of the fighting men, though they proved to be but effigies. 5 more days were occupied in travelling southward, the resting places being Penrith, Kendal, Preston and Chorley, the 2 travellers arriving at Chowbent on Sunday the 8th of February 1784. Mr. Cannon seems to have collected about him a little colony of Scotsmen, mostly from the same neighbourhood, and in the evening there was quite an assembly of them at the Bear's Paw, where Kennedy put up, to hear about the tidings from their native country brought by the last newcomer. On the following morning the boy began his apprenticeship as a carpenter with the firm of Cannon and Smith, serving 7 years for his meat and clothing. He applied himself to his trade and became a good, steady workman. He was thoughtful and self-improving, always endeavouring to acquire knowledge of the new arts and to obtain insight into new machines. Even in early life, said he, in the account of his career addressed to his children, I felt a strong desire to know what others knew, and was always ready to communicate what little I knew myself. And by admitting at once my want of education, I found I often made friends of those on whom I had no claims beyond what an ardent desire for knowledge could give me. His apprenticeship over, John Kennedy commenced business in a small way in Manchester in 1791, in conjunction with 2 other workmen, Sandford and McConnell. Their business was machine making and mule spinning, Kennedy taking the direction of the machine department. The firm at first put up their mules for spinning in any convenient garrets they could hire at a low rental. After some time they took part of a small factory in Canal Street, and carried on their business on a larger scale. Kennedy and McConnell afterwards occupied a little factory in the same street, since removed to give place to Fairbairn's large machine works. The progress of the firm was steady and even rapid, and they went on building mills and extending their business, Mr. Kennedy, as he advanced in life, gathering honour, wealth, and troops of friends. Notwithstanding the defects of his early education, he was one of the few men of his class who became distinguished for his literary labours, in connection principally with the cotton trade. Towards the close of his life, he prepared several papers of great interest for the Literary and Philosophical Society of Manchester, which are to be found printed in their proceedings. One of these, on the invention of the mule by Samuel Crompton, was for a long time the only record which the public possessed of the merits and claims of that distinguished inventor. His knowledge of the history of the cotton manufacture in its various stages, and of mechanical inventions generally, was most extensive and accurate. Among his friends he numbered James Watt, who placed his son in his establishment for the purpose of acquiring knowledge and experience of his profession. At a much later period he numbered George Stephenson among his friends, having been one of the first directors of the Liverpool and Manchester Railway, and one of the 3 judges, selected because of his sound judgment and proved impartiality as well as his knowledge of mechanical engineering, to adjudicate on the celebrated competition of locomotives at Rainhill. By these successive steps did this poor Scotch boy become one of the leading men of Manchester, closing his long and useful life in 1855 at an advanced age, his mental faculties remaining clear and unclouded to the last. His departure from life was happy and tranquil, so easy that it was for a time doubtful whether he was dead or asleep. To return to Mr. Fairbairn's career and his progress as a millwright and engineer in Manchester. When he and his partner undertook the extensive alterations in Mr. Murray's factory, both were in a great measure unacquainted with the working of cotton mills, having until then been occupied principally with corn mills and printing and bleaching works, so that an entirely new field was now open to their united exertions. Sedulously improving their opportunities, the young partners not only thoroughly mastered the practical details of cotton mill work, but they were very shortly enabled to introduce a series of improvements of the greatest importance in this branch of our national manufactures. Bringing their vigorous practical minds to bear on the subject, they at once saw that the gearing of even the best mills was of a very clumsy and imperfect character. They found the machinery driven by large square cast-iron shafts, on which huge wooden drums, some of them as much as 4 feet in diameter, revolved at the rate of about 40 revolutions a minute, and the couplings were so badly fitted that they might be heard creaking and groaning a long way off. The speeds of the driving shafts were mostly got up by a series of straps and counter-drums, which not only crowded the rooms, but seriously obstructed the light most required for conducting the delicate operations of the different machines. Another serious defect lay in the construction of the shafts, and in the mode of fixing the couplings, which were constantly giving way, so that a week seldom passed without one or more breakdowns. The repairs were usually made on Sundays, which were the millwrights' hardest working days, to their own serious moral detriment. But when trade was good, every consideration was made to give way to the uninterrupted running of the mills during the rest of the week. It occurred to Mr. Fairbairn that the defective arrangements thus briefly described might be remedied by the introduction of lighter shafts driven at double or treble the velocity, smaller drums to drive the machinery, and the use of wrought iron wherever practicable, because of its greater lightness and strength compared with wood. He also provided for the simplification of the hangers and fixings by which the shafting was supported, and introduced the half-lap coupling, so well known to millwrights and engineers. His partner entered fully into his views, and the opportunity shortly presented itself of carrying them into effect in the large new mill erected in 1818 for the firm of McConnell and Kennedy. The machinery of that concern proved a great improvement on all that had preceded it, and to Messrs. Fairbairn and Lilly's new system of gearing, Mr. Kennedy added an original invention of his own in a system of double speeds, with the object of giving an increased quantity of twist in the finer descriptions of mule yarn. The satisfactory execution of this important work at once placed the firm of Fairbairn and Lilly in the very front rank of engineering millwrights. Mr. Kennedy's good word was of itself a passport to fame and business, and as he was more than satisfied with the manner in which his mill machinery had been planned and executed, he sounded their praises in all quarters. Orders poured in upon them so rapidly that they had difficulty in keeping pace with the demands of the trade. They then removed from their original shed to larger premises in Mather Street, where they erected additional lathes and other tool machines, and eventually a steam engine. They afterwards added a large cellar under an adjoining factory to their premises, and from time to time provided new means of turning out work with increased efficiency and dispatch. In due course of time, the firm erected a factory of their own, fitted with the most improved machinery for turning out mill work, and they went on from one contract to another, until their reputation as engineers became widely celebrated. In 1826-7, they supplied the water wheels for the extensive cotton mills belonging to Kirkman Finlay and Company at Kettering Bank in Ayrshire. These wheels are even at this day regarded as among the most perfect hydraulic machines in Europe. About the same time they supplied the mill gearing and water machinery for Messrs. Escher and Company's large works at Zurich, among the largest cotton manufactories in the continent. In the meanwhile, the industry of Manchester and the neighbourhood, through which the firm had risen and prospered, was not neglected, but had the full benefit of the various improvements which they were introducing in mill machinery. In the course of a few years an entire revolution was effected in the gearing. Ponderous masses of timber and cast iron, with their enormous bearings and couplings, gave place to slender rods of wrought iron and light frames or hooks by which they were suspended. In like manner, lighter yet stronger wheels and pulleys were introduced. The whole arrangements were improved, and the workmanship being greatly more accurate, friction was avoided, while the speed was increased from about 40 to upwards of 300 revolutions a minute. The flywheel of the engine was also converted into a first motion by the formation of teeth on its periphery, by which a considerable saving was effected both in cost and power. These great improvements formed quite an era in the history of mill machinery, and exercised the most important influence on the development of cotton, flax, silk, and other branches of manufacture. Mr. Fairbairn says the system introduced by his firm was at first strongly condemned by leading engineers, and it was with difficulty that he could overcome the force of their opposition. Nor was it until a wheel of 30 tons weight for a pair of engines of 100 horsepower each was erected and set to work, that their prognostications of failure entirely ceased. From that time, the principles introduced by Mr. Fairbairn have been adopted wherever steam is employed as a motive power in mills. Mr. Fairbairn and his partner had a hard uphill battle to fight while these improvements were being introduced. But energy and perseverance, guided by sound judgment, secured their usual reward, and the firm became known as one of the most thriving and enterprising in Manchester. Long years after, when addressing an assembly of working men, Mr. Fairbairn, while urging the necessity of labour and application as the only sure means of self-improvement, said, "I can tell you from experience that there is no labour so sweet, none so consolatory, as that which is founded upon an honest, straightforward, and honourable ambition." The history of any prosperous business, however, so closely resembles every other, and its details are usually of so monotonous a character, that it is unnecessary for us to pursue this part of the subject, and we will content ourselves with briefly indicating the several further improvements introduced by Mr. Fairbairn in the mechanics of construction in the course of his long and useful career. His improvements in water wheels were of great value, especially as regarded the new form of bucket which he introduced, with the object of facilitating the escape of air as the water entered the bucket above, and its readmission as the water emptied itself out below. This arrangement enabled the water to act upon the wheel with a maximum effect in all states of the river, and it so generally recommended itself that it very soon became adopted in most water mills, both at home and abroad. His labours were not, however, confined to his own particular calling as a mill engineer, but were shortly directed to other equally important branches of the constructive art. Thus he was among the first to direct his attention to iron shipbuilding as a special branch of business. In 1829, Mr. Houston of Johnstown, near Paisley, launched a light boat on the Ardrossan Canal for the purpose of ascertaining the speed at which it could be towed by horses with 2 or 3 persons on board. To the surprise of Mr. Houston and other gentlemen present, it was found that the labour the horses had to perform in towing the boat was much greater at 6 or 7 than at 9 miles an hour. This anomaly was very puzzling to the experimenters, and at the request of the Council of the Forth and Clyde Canal, Mr. Fairbairn, who had already become extensively known as a scientific mechanic, was requested to visit Scotland and institute a series of experiments with light boats to determine the law of traction, and clear up, if possible, the apparent anomalies in Mr. Houston's experiments. This he did accordingly, and the results of his experiments were afterwards published. The trials extended over a series of years, and were conducted at a cost of several £1,000s. The first experiments were made with vessels of wood, but they eventually led to the construction of iron vessels upon a large scale, and on an entirely new principle of construction, with angle iron ribs and wrought iron sheeting plates. The results proved most valuable, and had the effect of specially directing the attention of naval engineers to the employment of iron in shipbuilding. Mr. Fairbairn himself fully recognised the value of the experiments,
and proceeded to construct an iron vessel at his works at Manchester in 1831, which went to sea the same year. Its success was such as to induce him to begin iron shipbuilding on a large scale, at the same time as the Messrs. Laird did at Birkenhead. And in 1835 Mr. Fairbairn established extensive works at Millwall on the Thames, afterwards occupied by Mr. Scott Russell, in whose yard the Great Eastern steamship was erected, where in the course of some 14 years he built upwards of 120 iron ships, some of them above 2,000 tons burden. It was, in fact, the first great iron shipbuilding yard in Britain, and led the way in a branch of business which has since become of first-rate magnitude and importance. Mr. Fairbairn was a most laborious experimenter in iron, and investigated in great detail the subject of its strength, the value of different kinds of riveted joints compared with the solid plate, and the distribution of the material throughout the structure, as well as the form of the vessel itself. It would, indeed, be difficult to overestimate the value of his investigations on these points, in the earlier stages of this now highly important branch of the national industry. To facilitate the manufacture of his iron ships, Mr. Fairbairn, about the year 1839, invented a machine for riveting boiler plates by steam power. The usual method by which this process had before been executed was by hand hammers, worked by men placed at each side of the plate to be riveted, acting simultaneously on both sides of the bolt. But this process was tedious and expensive, as well as clumsy and imperfect, and some more rapid and precise method of fixing the plates firmly together was urgently wanted. Mr. Fairbairn's machine completely supplied the want. By its means the rivet was driven into its place and firmly fastened there by a couple of strokes of a hammer impelled by steam. Aided by the jacquard punching machine of Roberts, the riveting of plates of the largest size had thus become one of the simplest operations in iron manufacturing. The thorough knowledge which Mr. Fairbairn possessed of the strength of wrought iron in the form of the hollow beam, which a wrought iron ship really is, naturally led to his being consulted by the late Robert Stephenson as to the structure by means of which it was proposed to span the estuary of the Conway and the Straits of Menai, and the result was the Conway and Britannia tubular bridges, the history of which we have fully described elsewhere. There is no reason to doubt that by far the largest share of the merit of working out the practical details of those structures, and thus realizing Robert Stephenson's magnificent idea of the tubular bridge, belongs to Mr. Fairbairn. In all matters connected with the qualities and strength of iron, he came to be regarded as a first-rate authority, and his advice was often sought and highly valued. The elaborate experiments instituted by him as to the strength of iron of all kinds have formed the subjects of various papers which he has read before the British Association, the Royal Society, and the Literary and Philosophical Society of Manchester. His practical inquiries as to the strength of boilers have led to his being frequently called upon to investigate the causes of boiler explosions, on which subject he has published many elaborate reports. The study of this subject led him to elucidate the law according to which the density of steam varies throughout an extensive range of pressures and atmospheres, in singular confirmation of what has before been provisionally calculated from the mechanical theory of heat. His discovery of the true method of preventing the tendency of tubes to collapse by dividing the flues of long boilers into short lengths by means of stiffening rings, arising out of the same investigation, was one of the valuable results of his minute study of the subject, and is calculated to be of essential value in the manufacturing districts by diminishing the chances of boiler explosions, and saving the lamentable loss of life which has during the last 20 years been occasioned by the malconstruction of boilers. Among Mr. Fairbairn's most recent inquiries are those conducted by him at the instance of the British Government relative to the construction of iron-plated ships, his report of which has not yet been made public, most probably for weighty political reasons. We might also refer to the practical improvements which Mr. Fairbairn has been instrumental in introducing in the construction of buildings of various kinds by the use of iron. He has himself erected numerous iron structures, and pointed out the road which other manufacturers have readily followed. "I am one of those," said he, in his Lecture on the Progress of Engineering, "who have great faith in iron walls and iron beams, and although I have both spoken and written much on the subject, I cannot too forcibly recommend it to public attention. It is now 20 years since I constructed an iron house with the machinery of a corn mill for Halil Pasha, then Seraskier of the Turkish army at Constantinople. I believe it was the first iron house built in this country, and it was constructed at the works at Millwall, London, in 1839. Since then, iron structures of all kinds have been erected: iron lighthouses, iron and crystal palaces, iron churches, and iron bridges. Iron roads have long been worked by iron locomotives, and before many years have passed, a telegraph of iron wire will probably be found circling the globe. We now use iron roofs, iron bedsteads, iron ropes, and iron pavement, and even the famous wooden walls of England are rapidly being reconstructed of iron. In short, we are in the midst of what Mr. Worsaae has characterized as the Age of Iron. At the celebration of the opening of the North Wales Railway at Bangor, almost within sight of his iron bridge across the Straits of Menai, Robert Stevenson said, "We are daily producing from the bowels of the earth a raw material, in its crude state apparently of no worth, but which, when converted into a locomotive engine, flies over bridges of the same material with a speed exceeding that of the bird, advancing wealth and comfort throughout the country. Such are the powers of that all-civilizing instrument, iron." Iron, indeed, plays a highly important part in modern civilization. Out of it are formed alike the sword and the ploughshare, the cannon and the printing press. And while civilization continues partial and half-developed, as it still is, our liberties and our industry must necessarily in a great measure depend for their protection upon the excellence of our weapons of war, as well as on the superiority of our instruments of peace. Hence the skill and ingenuity displayed in the invention of rifled guns and artillery, and iron-sided ships and batteries, the fabrication of which would be impossible but for the extraordinary development of the iron manufacture, and the marvellous power and precision of our tool-making machines, as described in preceding chapters. "Our strength, wealth, and commerce," said Mr. Cobden in the course of a recent debate in the House of Commons, "grow out of the skilled labour of the men working in metals. They are at the foundation of our manufacturing greatness, and in case you are attacked, they would at once be available, with their hard hands and skilled brains, to manufacture your muskets and your cannon, your shot and your shell. What has given us our Armstrongs, Whitworths, and Fairbairns but the free industry of this country? If you can build 3 times more steam engines than any other country, and have threefold the force of mechanics, to whom and to what do you owe that, but to the men who have trained them, and to those principles of commerce out of which the wealth of the country has grown? We, who have had some hand in doing that, are not ignorant that we have been and are increasing the strength of the country in proportion as we are raising up skilled artisans." The reader who has followed us up to this point will have observed that handicraft labour was the first stage of the development of human power, and that machinery has been its last and highest. The uncivilized man began with a stone for a hammer and a splinter of flint for a chisel, each stage of his progress being marked by an improvement in his tools. Every machine calculated to save labour or increase production was a substantial addition to his power over the material resources of nature, enabling him to subjugate them more effectively to his wants and uses. And every extension of machinery has served to introduce new classes of the population to the enjoyment of its benefits. In early times, the products of skilled industry were for the most part luxuries intended for the few, whereas now the most exquisite tools and engines are employed in producing articles of ordinary consumption for the great mass of the community. Machines with millions of fingers work for millions of purchasers, for the poor as well as the rich. And while the machinery thus used enriches its owners, it no less enriches the public with its products. Much of the progress to which we have adverted has been the result of the skill and industry of our own time. Indeed, says Mr. Fairbairn, the mechanical operations of the present day could not have been accomplished at any cost 30 years ago, and what was then considered impossible is now performed with an exactitude that never fails to accomplish the end in view. For this we are mainly indebted to the almost creative power of modern machine tools, and the facilities which they present for the production and reproduction of other machines. We also owe much to the mechanical agencies employed to drive them. Early inventors yoked wind and water to sails and wheels, and made them work machinery of various kinds. But modern inventors have availed themselves of the far more swift and powerful, yet docile force of steam, which has now laid upon it the heaviest share of the burden of toil, and indeed become the universal drudge. Coal, water, and a little oil are all that the steam engine, with its bowels of iron and heart of fire, needs to enable it to go on working night and day, without rest or sleep. Yoked to machinery of almost infinite variety, the results of vast ingenuity and labour, the steam engine pumps water, drives spindles, thrashes corn, prints books, hammers iron, ploughs land, saws timber, drives piles, impels ships, works railways, excavates docks, and, in a word, asserts an almost unbounded supremacy over the materials which enter into the daily use of mankind, for clothing, for labour, for defence, for household purposes, for locomotion, for food, or for instruction. End of chapter 16. End of Industrial Biography, Ironworkers and Toolmakers by Samuel Smiles. Read by Clive Catterall. June 2018, Hereford, England.